should listen to all the sessions very carefully, because we will be having a QA session at the end of all these sessions, and you will be getting praises those who can answer those questions. So I request all the students, yeah, of course, including faculty members, to focus on the presentations and try to digest whatever the resource persons are explaining. Now our first session will start. The first session is on radiation detection and measurements by Dr. Savyasai Patra. So now I welcome Dr. Savyasai Patra Garu to deliver his lecture.
So, good morning to all of you. So, welcome to the third technical day, the morning session. So, during the last 2 days we discussed the fundamental of radioactivity and decay laws, and the nuclear structure and stability. But now this day we are moving towards the practical aspects majorly. In fact, yesterday Dr. Atanu Jha covered all the fundamentals of interaction of radiation with matter. So now you know that how radiation, different kinds of radiation, how they interact with matter. So that property we can actually use to detect them, because if we choose suitable detector material, and by virtue of how the incident radiation is interacting with the detector material, one can actually detect them and develop radiation detectors. So our today's focus is to understand the radiation detection and mechanisms, because this is very useful if you work in any branch of nuclear science, and particularly in nuclear physics. This is your tool. So in your toolbox you have different kinds of radiation detector. So depending upon your application, you are going to choose a certain type of detector. Okay. So like every day, our today's learning objectives should be to have a foundational understanding on the general principle of detection and measurements, okay, and then the block diagram of a counting system, that what are the principal component of a counting system, and then I will majorly cover these 3 kinds of radiation detector, that is the gas field detectors, scintillator detector and the semiconductor detector. And I will be briefly discussing in which situation you are going to choose which kind of detector. So when I say detection and measurement, the general principle is radiation while passing through matter may interact with matter, and if it interacts, then a device should be there upon which when it interacts it should sense the interaction. Okay. If it does not sense the interaction, then there is no detection. So first is it should sense the interaction from radiation and converts the interaction to a measurable signal. Okay. So for that we need certain instrumentation which consists of electronic circuits to amplify, analyze, count and display the useful results. So as you can see in this schematic, like you have a radiation source. So in front of the radiation source you have some kind of detector, but the detector alone cannot be sufficient. So you need certain electronics to measure the produced signals. We will discuss in more detail. So, what is the aim for radiation detection? Why do you want that? The aims are to first understand, is there any radiation or not at gross level, and if it is there, then the second curiosity is what is the type of the radiation, and then what is the level of the radiation, and then for further more curiosity, what is the energy of the radiation, and then further we try to identify what is the source of the radiation, like which isotope is actually responsible for emitting that particular kind of radiation that is being detected. So, it is important for identification, characterization, and finally assay of radioactivity. So, in context of your research in various branches of this nuclear science, very frequently you will need to assay radioactivity present within your sample. So, there are different challenges that maybe we will see in a couple of slides later, but for all these purposes what you need is radiation detector. So, without that you cannot. And operation of radiation detectors involves interaction of radiation with material of the detector. In fact, it is not only restricted to nuclear science alone, like radiation detector is there in fact all branches of science. Like all of us use different kind of radiation based characterization technique nowadays. We do a lot of, like in materials also we do a lot of use X-ray for X-ray diffraction, we do neutron diffraction and all this kind of thing. Actually we need to have radiation detectors. So, operation of radiation detector involves interaction of radiation with matter, which Dr. Atanu has already covered nicely last day, and deposition of energy, ionization, excitation mechanism, that also Dr. Atanu covered very well. So, it forms the basic signal, and that we will be concentrating here on. So, let us try to very simply understand that what happens when radiation is falling into some detector material. So, when radiation interaction with detector material, it causes the appearance of electric charge within the detector active volume at time t is equal to 0. As Dr. Atanu mentioned yesterday, whenever some radiation interacts with some material, if it is ionizing radiation, there may be ionization or excitation. So, if there is ionization, there is the formation of some, let us say if it is a gas, neutral gas molecule, when there is some ionization, it forms like electron and the positive ion of that molecule. So, it appears some electric charge within the detector active volume. So, let us say at time t equals to 0, and then by applying some potential you actually collect those charge. Okay. So, there is some charge collection. So, let us say this Tc is the charge collection time. So, you actually generate the charge you actually develop the charge in the active volume. So, the current is produced, and this current is basically again come to 0 when the charge collection is completed. So, there is some charge collection time characteristic of a system. So, if you integrate this IT over dt between 0 to Tc, that gives you the total charge. Okay. So, Tc may vary between a few nanoseconds for semiconductors to a few milliseconds for ion chamber. So, depending upon the system, the charge collection time may vary. So, in reality what you observe is, let us say radiation from many different sources are incident on a detector. So, actually you get this kind of current pulses of different size over time, and then what you do is different depending upon the situation and your objective, you can choose the mode of detector operation. So, basically there are two different mode, like current mode and pulse mode. I will be very briefly discuss what is current mode. This you all actually understand and know probably, that whenever this detector is, now I am incidenting with some radiation, as I just mentioned that the charges are produced and you are collecting the charge. So, this is from, so what you measure in current mode is, it is very difficult to distinguish them, that what we are seeing here, what we are seeing here. Rather what you do is you measure a average current. Okay. You measure a average current over time. So, it is like this 1 by T and then this integral total current. So, this T is nothing but the measurement time. Let us say I do, like in the practical also you are measuring this GM counter for 30 seconds, 60 seconds, 100 seconds. So, that is your T, and for that entire time whatever we as the integral count, we are just making them average out. So, this is giving you the black dotted line. So, the average count you are measuring. But in pulse mode, it is important when you are interested in doing some spectroscopy. Let us say when you are using that sodium iodide detector in the other practical. So, this pulse mode, it records each individual interaction of the radiation with the detector. So, it is used for radiation spectroscopy. So, when you are interested in spectroscopy, that means you are interested in identifying, let us say if it is a gamma ray, you are interested to identify which energy gamma ray actually you are detecting. Okay? So, that actually helps you to identify the source. So, which is the measurement of the energy of individual radiation quanta. So, here you can see this is slightly different, where actually the detector and preamplifier and the cable, they have some some capacitance for the detector and the cable used to connect the detector and the preamplifier, and there is some load resistance in that system. So, this combined is RC is called the time constant of the detector. So, in this situation there may be different scenario, like as you can see, for example, this is your current pulses. So, when you are seeing that, let us say there could be two different cases. Your timing constant of the detector is very short, it is much less than the charge collection time of the detector. So, in that case actually the current flowing through this R is equal to the current flowing in the detector. But this is the most important one which we most frequently use, that timing constant of the detector is greater than the TC. In this case what you do is, while the charge is being collected, the capacitor is charged, and once the total charge is collected after this TC, the capacitor actually discharge. So, during the discharge there is a potential drop across the load resistance, and that gives you the signal. So, this rise of this pulse depends on the time, this detector charge collection time. So, it is a property of the detector, and this decay time depends on the timing constant of the load circuit. So, it is the circuit property, circuit dependent. Okay. So, if we look at the block diagram of a counting system, I can see that I have a detector, and of course, I need to apply some high voltage in order to collect these charges, and then the detector should be immediately accompanied with a preamplifier and then an amplifier, then it is connected to some multi-channel or single channel analyzer. We need to amplify the signal because the pulses that is produced because of this radiation is very short. So, we need to amplify them in order to detect. So, signal is generally small, it has to be amplified and then processed. A very interesting figure, that is called the pulse height spectra, that is very useful whenever we are interested in doing spectroscopy. So, what you see here is two different kind of pulse height spectra. One is called the differential pulse height spectra, another is called the integral pulse height spectra. So, in differential pulse height spectra, what you see is, you can see this is the pulse height. So, pulse height is nothing but the amplitude of the voltage pulse that is produced, and you are kind of making a histogram out of that D and DH. So, what you can see is, at the full energy you have a peak like feature, and after that of course very many different short pulse is there due to several reasons. That is, for example, Dr. Atanu explained yesterday that there are Compton effect and the photoelectric effect when you talk of gamma ray detection. So, for Compton scattering the energy is not fully transferred. So, you have some contribution at the lower energy, lower pulse height compared to the photo peak. And once you look at the integral pulse height spectra, you can see this. So, the slope at the integral pulse height spectra is basically giving you the amplitude. And here also I am coming to the concept of this pulse height discriminator, that also I think in your practical you did already, that this gain is very important. Like for example, in order to distinguish the real pulse from the electronic noise, you need to apply certain gain to amplify the signal to higher pulse height. For example, you can see if this HD is my pulse height discriminator, this at gain 1 my measured signal pulse is actually merging with the electronic noise and we are not detecting anything. But as you increase the gain, you see at gain 2 your pulse actually shifting to the higher pulse height, at gain 3 it further shifting to higher pulse height. So, it gives you the counts in the measurement. So, that way actually you generated this GM plateau, right. You did your experiment in GM. So, you kept on actually increasing the applied voltage, okay, by applying the applied voltage, you actually shifted it to higher and higher and attained a plateau. So, in some type of detector such as GM counter or a scintillation detector, the gain can be varied by changing the applied voltage to the detector. Now, what are the characteristics of an ideal detector? It is the deposition of the radiation energy should be fast and complete, and charge generated preferably proportional to the energy, and the collection and measurement of the charge should be as fast as possible to identify the following successive events, otherwise the dead time will increase. So, it should have small dead time. So, that is a good detector. Now, I am coming to a concept of energy resolution that is very important whenever we talk of radiation spectroscopy. You imagine that we are talking of, like, for example, at a given energy of radiation, if it is creating some charge pair in my system and I am collecting the charge pair every time. So, can I say that every time this radiation interacting with my detector material, if it produce every time equal number of charge and all the charges if they are effectively collected, then in principle I should get a delta function kind of pulse height spectrum, because every time I should have the pulse of same height. But in real life it is not so simple. So, in real life you do not get a delta function, but you get a distribution that we already did in the practical of GM counter statistics, right. So, as you know that the radioactivity is always a statistical phenomena, because all the interaction does not create same number of ion pairs, and as it does not create same number of ion pairs every time, even if you completely collect all the charges, you do not collect same number of charge, and so you do not produce every time the signal of same amplitude. So, that actually brings a distribution in the pulse height. So, a detector with a good resolution will give you a peak with narrower distribution, a detector with poor resolution will give you the signal with broader distribution. So, this resolution therefore means the ability for a detector to resolve two adjacent signals. Okay? Two adjacent pulse height, let us say you have gamma rays of two different energy. So, how good you are able to resolve them. So, for example, you have a distribution like this and the mean pulse height is around 80. So, you define a property called full width at half maxima, that is you define at 2.35 into the sigma. Sigma is the standard deviation. Okay. So, you see this 80 is basically proportional to the n. So, you more it is the number of this n, the total number of charge carrier generated on an average, that decides the pulse height, right. You have more number of charge carrier, you have higher pulse height, you have less number of charge carrier, you have lower pulse height. So, if you put some proportionality constant, this H0 is kind of Kn. So, you can write this sigma, as we already learned in the GM practical, that this standard deviation is basically the square root of your total number of events, right. So, this k square root of n you can write for sigma. So, you can simplify the expression for FWHM as 2.35 k square root of n. So, the resolution, which is basically defined as a dimensionless fraction, which is FWHM divided by the pulse height, and if you want to quote the percentage resolution, so you multiply it with 100. So, here if you replace this H0 with this Kn and this FWHM you replace with this 2.35 k square root of n, you end up getting a 2.35 square root of n. So, you can imagine that it is a function of the n. So, more is the number of charge, more is the number of this n, you have a better resolution. Okay. So, a detector which actually produces more number of charge pair for a given amount of radiation, for it the resolution is better. So, we will come to comparison between different detector resolution and all. Yes. So, here itself. So, for example, you see we have a germanium detector which is a solid state semiconductor detector, and a sodium iodide detector which is basically a scintillation kind of detector, because these two detector does not have different resolution. You can see that it is reflected in their spectrum. So, you can see that the sodium iodide spectrum is much broader compared to the germanium spectrum, because in case of germanium the number of charge pair produced is much high compared to the sodium iodide detector. So, what are the sources of poor resolution then? It is the statistical fluctuation in the number of charge carrier produced, as I just mentioned, and then the incomplete collection of charge which is produced after interaction of radiation in the detector, and of course, the electronic noise should be low in order to have a good resolution detector. So, then comes another very interesting property of a detector, that is called the detection efficiency. Okay. So, by this word efficiency we can actually, we know it is a, if we go by simple dictionary meaning, the efficiency means its ability to perform some job. Okay. So, you are very good, you are very efficient means you perform it very good. So, a detector is very efficient means a detector actually detect the radiation better. A detector with poor efficiency means it is not so good in detecting the radiation. Like for example, if 100 radiation is incident on a detector, out of which actually how many is detected, it is that kind of factor. So, you just come to understand here, let us say absolute efficiency and intrinsic efficiency, we define it in these two terms. So, absolute efficiency means it is the number of pulses recorded and the number of radiation quanta emitted by the source, the ratio of that. So, for example, here the source, let us say it is you and you are just throwing 100 balls in randomly in all direction, okay, and here is the someone else is standing who is the detector and his job is to catch these balls. So, let us say I am the source, I am throwing out 100 balls in random detector in random direction, and you being standing there, you are able to catch only 5 out of them. So, the efficiency of absolute efficiency of you being a detector is only 5%, followed. So, the absolute efficiency is that simple, like the radiation actually is emitted in 4 pi direction in all the direction, but the detector can only detect some of them. Okay. So, that ratio is basically the absolute efficiency of the detector, and the another is the intrinsic efficiency, which is defined as the number of pulses recorded by the number of radiation quanta incident on a detector. So, it is more fundamental property of the detector, because now forget about the balls thrown in all the direction, but let us say the ball thrown in all the direction and out of which actually 10 ball actually come in contact with the detector, but out of which only 5 was detected, then its intrinsic efficiency is only 50%, followed. So, you will come to understand it with this figure, it is better. Let us say this is the source. So, it is emitting the radiation in all the direction, okay, out of which only let us say a few fraction is detected. So, that is the absolute efficiency, and let us say 10 out of all this radiation has reached the detector, but out of which only 2 is detected, then it is 20% intrinsic efficiency, followed. But this absolute efficiency and the intrinsic efficiency, they are having some geometrical relation, and it is written as intrinsic efficiency is equal to the absolute efficiency into this 4 pi by omega. So, here the omega is basically the solid angle subtended by this cone, okay, which is nothing but this pi a square by d square. So, once you know this, so another very useful efficiency, it is basically the absolute efficiency, but why I am making you introduce to this term full energy peak efficiency, because for your research mostly when it is a question of quantifying certain radionuclides, what you are interested mostly on the full energy peak area, okay. So, the efficiency of full energy peak means suppose you have a gamma ray of energy E. So, at the pulse site who are generated for the complete E energy deposition, this is called the full energy peak. So, that only can be used for quantification purpose. So, as I wrote, only those interactions that deposit the full energy of the incident radiation is counted. So, it is the most meaningful for radiometric assay. Now, I am coming to one by one different type of radiation detector. Okay. So, I will first start with gas field detector. In gas field detector, I will mainly discuss this 3 kind of detector, that is the ionization chamber, proportional counter and the GM counter. So, out of which this GM counter you are already using during your practicals, and then I will touch upon the scintillation detector, which is basically inorganic and organic scintillator I will discuss, and then I will come to the semiconductor detector. So, with these let us come to the gas field detector. Now, you can see that the gas field detector is very simple. You have a metal cylinder, okay, and inside that you have some anode material which is also a metal wire, and you connect these two in the two different terminal of a battery. So, you see when this ionizing radiation is actually falling on your detector material, let us say it is filled with some gas, okay, let us say it is argon or air or any other different gas. When it is interacting with these gas molecules, if it is ionizing radiation, it may cause excitation or ionization. If it produces ionization, you can imagine that there may be electrons and the positive ion of the gas molecule. So, when you apply this voltage, so then what will happen? The electron will actually move towards the anode and the positive ions will move towards the cathode, and they will get collected. So, when they move towards different direction, it gives you some measured signal, right. So, once you have this measured signal in current mode, you can take such average current over time and you can get a gross signal, okay. So, if you look at this figure, this will make you understand the different region of applied potential, and a different applied potential, how the characteristic of the gas field detector it changes. So, let us say that you do not have any applied potential, you just have a field gas, you just put radiation. So, what will happen? The ionizing radiation, it will certainly ionize the gas molecule, but because you do not have any applied potential, they will immediately get recombination, right. So, they will not be separated. So, if you do not have any applied potential, you do not have any pulse amplitude, you start from 0 because you are not collecting any charge. Now, you imagine that you are slowly increasing the applied potential, okay. Just remember your Geiger-Müller counter practical, that what is the first practical? To find the plateau. So, you slowly increase the potential, right, and you keep on noting the data. So, as you see that you start slowly increasing the potential, you start slowly getting the pulse amplitude increasing. So, in this region there is a competition between the ionization and recombination, because you applied some potential. So, you started collecting the charges, but at the same time there is a possibility of recombination also, okay. You are not able to completely collect the charges unless you attain a certain voltage at which the recombination is now become insignificant. So, that is why this plateau region, when you are reached, you actually all the ions are collected by the respective electrodes. So, your recombination is now not possible beyond this certain applied voltage. So, that region is called the ion saturation, and actually you can run this, you can use this ionization chambers, who are basically current mode of detection in this region, okay. And then let us say you further increase the applied voltage, what will happen? This gas multiplication will start. I will just come in a while what is gas multiplication, but this gas multiplication will come means this electron and the positive ion that are being generated in the primary interaction. Now, because the applied potential is high, this electron can again further ionize another gas molecule to produce another cation and the electron, and that way it can further, so subsequently it can form an avalanche or a chain reaction of this ionization, and therefore its pulse amplitude now kept on increase proportionately, okay. Because it kept on increasing proportionately, so it called the proportional region, and in this region the gas multiplication can reach up to a multiplication factor of 10 to the power 6 to 10 to the power 4, okay. Now, if you further increase this applied voltage, this proportionality you will now start losing. This proportionality you will start losing because beyond certain applied potential, now you will have secondary event generation, like from one primary interaction you had one avalanches, but it may so happen that one of the interaction actually did not make ionization, but you had excitation, and during the de-excitation of that particular gas molecule it may emit some ultraviolet kind of radiation, and this radiation may again further make another ionization, so you lose the proportionality. Now you do not have any proportional actually estimation. So that's why this region is of no use, it is called the limited proportionality region. So as you imagine these two lines, one is for 1 MeV, one is for 2 MeV radiation. So when your energy is high, you have more and more pulse amplitude. So they were running parallelly up to this, but when they started losing this proportionality, this energy dependence now being reduced. So you no longer have any energy dependence, no longer have any proportionality. So this is called the limited proportional region, and this region is of now no use for you. Beyond a further certain applied voltage, the energy dependence actually diminishes. So you imagine like either it is the same radiation of different energy, or you can imagine that one is alpha, one is beta, it does not matter. But beyond this potential voltage, it does not have any difference. So whatever kind of radiation it is coming and making some ionization, it is producing some signal, but it is not able to distinguish them, but you do not have that proportionality anymore. So beyond this region, this pulse height again increases after this applied voltage, and then attain a kind of plateau, and this is the Geiger-Müller region. Okay. So in Geiger-Müller region, you actually generate the secondary pulses and avalanches spread across everywhere. I will just show you in more detail little later. So in this region actually, so in this region you have a very strong avalanche effect across the detector volume. Okay. So for example, this ionization chamber which works in ion saturation region, it is simplest of all the gas field detector. Generally the gases used as argon, helium, air. Due to less number of charge carrier, they have the poor energy resolution and are mostly used for radiation monitor, dosimeter. They are mostly operated in current mode, this I already told you. The proportional counter, the electrons are accelerated by the applied field. If kinetic energy of electron is greater than the binding energy of electron in the medium, then they cause further ionization, what I discussed as gas multiplication. And then threshold electric field strength. Yeah, so threshold electric field strength needed to initiate this gas multiplication is around 10 to the power 6 volt per meter at 1 atmosphere, and total charge collected is proportional to the original number of ion pairs. So you maintain some proportionality, and that is why you use this as a proportional counter. And you have mostly commonly used field gases is 90% argon and 10% methane. This methane is basically is a quench gas which is used because, as I just mentioned in the last slide, that you have excitation as a parallel mechanism always. So this during the de-excitation there may be some emission of this ultraviolet radiation which may cause further ionization. So you want to actually quench that excitation, you do not want radiative de-excitation. At the same time, after that electron is actually collected, and then it is again in the circuit, it is coming to this cathode and this recombining with the argon positive molecule. So during this recombination also there may be some radiative de-excitation. So that light again can trigger further ionization. So those kind of event you want to suppress. So you need to add some quench gases, and then the energy resolution of a proportional counter is in the range of 5 to 10%. They are mostly operated in pulse mode. They are used in the form of gas field or gas flow counter for alpha particle and fission fragment counting. Now here I will discuss a little bit detail, like for example, if you see that electrons are collected in this anode wire. So let us say this anode wire is having a radius of A, and let us look at that how this electric field that is generated across the anode wire actually behave. So if you see that this electric field is basically having a relation like V by RL and V by A, where this V is the voltage applied between the anode and the cathode, A is the anode wire radius, B is the cathode inner radius. So you will see that the electric field is very strong in very near vicinity of this anode wire. Okay. So even though we have a big GM counter, but my gas multiplication in this proportional region is only happening to very close vicinity of this anode wire. So for example, you can see here that let us say this is your anode wire. So let us say from here, because the potential is actually meeting the threshold potential for avalanche formation. far from that anode where you do not have the threshold potential to meet this avalanche formation criteria. So, very near to this anode where actually you start making the avalanches. So, these are the Monte Carlo simulated data where actually you start seeing, let us say you start the ionization here, and here one electron it makes 2 electron, 2 makes 4, 4 makes 8, like this, like that. So, what you detect finally at the anode wire is a lot of electrons. So, as I said, the multiplication factor is around 10 to the power 4 to 10 to the power 6 electron actually you detect for one ionization. That much multiplication it is possible to achieve in proportional region, and each electron here undergoes the same multiplication process regardless of its original position or the formation, and the multiplication factor will be same for all the original ion pairs. That is why it is called the proportional region. So, each original electron leads to an avalanche which is independent of all other avalanches formed in the electron, formed from other electron, and collected charge remains proportional to the number of original electrons. Now, in the further increasing that applied potential, when you enter the GM region, what happens is high electric field in a GM tube intensify each avalanches. Now, as I was telling that now each avalanche may again create a secondary avalanches and so on. So, under specific conditions one avalanche can trigger another at a different location. So, for GM now this condition actually is not met, that the proportionality will be there, but at a critical electric field each avalanche create at least one more leading to a self propagating chain reaction. Okay. So, now you imagine that self propagating chain reaction has started. So, then does it never stops, because it is a self propagating chain reaction. So, when does it stop? It stops because within this detector the electrons actually move very fast. So, they are collected much faster at the anode wire, but the positive cation they move slowly and they kind of keep on accumulating near the cathode surface. So, when these positive charges keep on accumulating in the positive near the positive cathode as kind of space charge, you can imagine. So, they actually reduce the potential, right. So, the electron which were earlier going very fast towards the anode wire, now we have some opposite direction pull also because of the too much of positive charge accumulation near the cathode wire. So, the electron gets slow down and finally it lose the kinetic energy required to create further ionization. So, the further ionization stop. Okay. So, beyond a certain level of multiplication it has to stop, and that way it always stop after a certain level of amplification. So, at a critical electric field each avalanche create at least one or more leading to a self propagating chain reaction, and this high voltage creates enough positive ion near the cathode as I just mentioned, which reduces the electric field and prevent further gas multiplication. So, you can see that what happens in this GM region. So, let us say as I was saying here some ionization took place. So, it actually created the avalanches you detect here, but in the meantime you may have emission of UV radiation due to the de-excitation in a radiative pathway. That UV can create further avalanches, it can interact with the cathode material, generate electron, it can also responsible. So, from all different sources actually you create avalanches as long as you do not have sufficient space charge accumulated near the cathode surface and you stop making further avalanches. Okay. Clear? So, the mechanism by which these additional avalanches are triggered in a Geiger discharge is shown here. So, the limiting point is reached after a similar number of avalanches every time, as I just mentioned that it is limited by the formation of the space charge, and a Geiger tube can only count radiation event, it does not measure the energy, it making it unsuitable for direct radiation spectroscopy, because it does not have any proportionality with the amount of radiation, with the energy of the radiation, because the energy dependent actually diminishes. So, it does not it cannot be applied for spectroscopy, and GM counter cannot distinguish between different radiation types. So, high gas multiplication factor is a big advantage in simple radioactive counting. So, let us say very low level counting also can be possible, because one incidence actually create a huge multiplication, and simple low cost ease of operation as you already witnessed in your practical. Helium, argon can be used, detect alpha, beta, gamma, any ionizing radiation. Quencher is important to add, otherwise you will have too much of this secondary events and high dead time. High dead time is the limitation, as we have determined the dead time in the practical classes. So, now you can recognize your instrument. Already 2 groups have used this instrument, so you know how simple it is to operate. Today also some group will use. To make you understand the concept of dead time, as we already determined during your practical, you obtain some dead time on the order of microsecond. So, if you see that, let us say you have this initial full Geiger discharge. So, let us say your one radiation interacted with a GM tube, it produced some electron ion, produced further avalanches like that, you collected all the electrons. Okay. So, you collected all the electrons means your signal is generated. So, you got the signal, but so that actually is the this time, this is the dead time. So, the time until which the charge collection is taking place, till then your detector is dead. Your detector is dead means till then another radiation which will fall in the detector, it will not get detected. So, that is the dead time of the detector. But in reality, as I just mentioned few slides back, that the positive space charge they get accumulated near the cathode surface. So, they actually reduce the applied voltage. So, if you even if you think that I have applied this V potential voltage, but because of the space charge effect, the effective applied potential is now less. So, that is why just after the dead time, even if some radiation interact with the material, it will give you smaller signal because it is experiencing lower potential. But with time, this space charge also tend to then get disappearing, and with time again the applied potential will tend to restore. So, it will take some time, which is called the recovery time of the detector, and after a certain time of another few microsecond, another 100 microsecond, let us say, it will come back to its original state. Like if you have applied V, then it is V, it is not less than V. So, again you will then get the pulse of the similar height. So, you can remember, you can now visualize that even though if you have a dead time of around 100 microsecond, your actual recovery time is around 200 microsecond. So, you can imagine that this is the limitation of the GM counter, like it needs 200 microsecond in between 2 radiation quanta to be detected properly. Okay. So, you can see here that the Geiger counting plateau, how it is reached. So, as our Mr. Sahir Alam demonstrated you, that as you keep on increasing the applied voltage, like for example, you see 1000 volt, 1200 volt, you actually shift your signal beyond that discriminator, and then only you actually start seeing the signal. So, if you have voltage which is not sufficient, you do not have any signal. So, initially you used to get 0, 0, 0 reading, this kind of reading you get in GM tube, but after a certain applied voltage you actually get this kind of plateau. Okay. Now, I am switching to scintillation detectors. So, this is another type of detector, radiation detector, which is mainly used for radiation spectroscopy. This is a either solid state detector or liquid detector. I will be discussing both. So, it works by using materials that emit flashes of light. This emission of flashes of light, this phenomena is called scintillation. So, this is basically nothing but the fluorescence that you already probably are much aware of, and when exposed to ionizing radiation. So, these light flashes are then converted into electrical signal by a photodetector for measurement. So, there are different kind of photodetector, you may be already aware. So, the common scintillator materials in inorganic are, for example, this sodium halide. So, it can be sodium iodide thallium, it is cesium iodide, bismuth germanate, barium fluoride, different materials are available, like it is a n number of material which acts as scintillator. Similarly, in organic also, any kind of aromatic molecules which have conjugated pi double bond. So, they are quite useful material for using as a scintillation. So, such few examples are like anthracene, steel beam, different kind of plastic scintillators are available, liquid scintillation cocktail, they are commercially available. So, when you choose solid, when you choose liquid, that is a purely based on the application, I will just discuss. So, for example, if you want to detect alpha radiation, mostly you prefer to use this organic, because you just mix the activity with organic. I will just come in the next slide. So, what are the requirement for a good scintillator? it should convert as large a fraction as possible of the incident radiation energy to prompt fluorescence. Okay. It should not have much of, it should minimize the undesirable contribution of phosphorescence and delayed fluorescence. So, the material for which the fluorescence yield is high, that is a good scintillator material. Okay. For example, you can see here that the energy liberated in de-excitation emitted as light, that is called the scintillation light, light channeled to photomultiplier tube. So, photomultiplier tube is basically a photon detector which can detect light photons, and this light at the detected a photocathode, it produces some photoelectrons. Now, these photoelectrons get multiplied at different dianode material in the PMT and finally collected at the anode after the last dianode and give you a signal. So, the light is converted into electrical signal in a photomultiplier tube. So, energy required per photoelectron produced in this kind of scintillation detector is around 300 electron volt. So, which is high compared to the germanium based solid state detector, that is why it is having a poor resolution. So, resolution of 662 keV for a sodium iodide detector is around 5 to 10%, and different materials are used as a photocathode and diode. They are commercially very standard materials, bialkali materials, these are used. But there are few more requirements in order to be a very good scintillator material. It should have high scintillation efficiency, it should have light yield proportional to the deposited energy, it should be transparent to the wavelength of its own emission, it should not have much of self quenching. Okay. It should have a refractive index which is comparable to that of glass, because the PM tube window is made of some glass molecules, so glass. So, if your light emitted by the scintillator, if it do not pass that window very well, then you lose the photons. So, you produce less signal. It should be manufacturable in large size. Suppose you want to make high efficiency radiation detector, you should able to manufacture the crystal in large size, and high density and high atomic number material should be used, because mostly they are used for, particularly for gamma spectrometry application, it is very important criteria that high jet material must be there to have, as Dr. Atanu already mentioned, that this probability for this gamma interaction with matter is very much dependent on the jet of the material, right. Here I show you some examples of organic scintillator. So, as you see that anthracene is the one of the oldest organic material. So, you can see this is the anthracene molecule which belong to the class of polycyclic aromatic hydrocarbon, which is having 3 benzene ring associated in a conjugation. Another very useful material is stilbene. You can see the structure of trans stilbene here. Scintillation cocktails, they are commercially available, okay, of different brand. So, different other way you can actually make your own scintillator also by taking some organic solvent. Typically you take like different organic solvent and then you take scintillator molecule which are very well known commercially, like for example PPO, that is 2,5-diphenyl oxazole, this kind of molecule which is having a very good fluorescence response, and then because its decay wavelength is slightly higher energy compared to what actually PMT can detect very well. So, use some kind of wavelength shifter. So, what you do is the emission of this 2,5-diphenyl oxazole, it further excites this pop-up molecule, and finally this emission from the pop-up molecule we actually detect in this scintillation. So, you can prepare this scintillator like this. You can prepare scintillating membrane by casting this polymer inclusion kind of membrane using this kind of molecules within it. So, there are many possibilities. They are also used for simple alpha beta counting. Let us imagine that this is a conventional alpha beta counting detector where you can see this black two are 2 different PMTs. So, 2 different PMTs, and in between you see there is a hole to actually put your sample inside in a scintillation vial. So, inside the scintillation vial you just put that scintillation liquid or scintillation cocktail, you add the alpha activity inside this. Okay. So, you see that when the alpha activity is completely dissolved within the scintillation cocktail, so you do not actually lose any of the radiation. So, it is 100% efficiency, whatever light it is generating, you see the geometry, all are detected by this 2 PMT. So, it is 100% efficiency for alpha. So, even a very very small amount of activity it is possible to detect using this. If we look at inorganic scintillator, it is the alkali halides, as I mentioned, are the most widely useful. They are insulator and have wide gap between the valence band and conduction band, suitable activator are used like thallium to create excited states which decay by emission of light in the visible range. Sodium iodide thallium detector is the most widely used scintillator for gamma counting, and other scintillators are also possible. Okay. So, this is the role of the activator molecule. Like activators, they create actually special site they call illumination center in the lattice of the basic crystal sodium iodide, let us say, and in the lattice at which the normal energy band structure is slightly modified from that of the pure crystal. So, you emit the visible light. Okay. So, it is like the electron hole pair, they actually that exciton, they are actually freely sometimes can get into the activator site and then cause the de-excitation from the activator states only, and that way you emit at the visible region. So, here you see the photograph of typical sodium iodide thallium detector that you have already used in your practical. So, it has a emission wavelength of around 410 nanometer, excellent lighted, linear over most energy range, but the limitation is this crystal is little brittle, they are hygroscopic, so need to be kept in vacuum. And of course, the property of the PMT also, you know, it is typically the amplification it makes is around 10 to the 6 and its response time is nanosecond. Okay. Now, I am coming to almost towards the end of this lecture. I am just cover the semiconductor detector. So, in semiconductor detector, it is used to detect ionizing radiation using semiconductor. So, it is kind of the best detector, but it is having, you know, it is costly. So, it is it costs, like because of this nature, like it is there are challenges to prepare very high purity semiconductor material. You will just realize, I will just tell you. So, it is a solid state detector. Silicon and germanium semiconductors are conventionally used as radiation detector material. So, it is 3 electron volt, like in sodium iodide we told 300 electron volt. So, here it is 3 electron volt which is required to produce a charge carrier pair. So, you can imagine the 100 times more charge carrier can be produced, and then the large number of charge carrier are produced compared to sodium iodide. So, therefore, it is having a good energy resolution, and then P and N type of semiconductors are generally used. Now, let us try to understand that the semiconductor detector, they actually works in the principle of p-n junction. Okay. So, let us imagine that you have a n type semiconductor and you have a p type semiconductor, they are separately kept. This you people are physics people, you may be already, you must be knowing that n type of semiconductor means you have some donor impurity, p type of semiconductor means they have some acceptor impurity. So, in their band structure, in the n type of material you have some donor ions as impurity, in type of p type you have some acceptor ions as impurity. Now, what is interesting is that when you make them touch each other, touch means it is not a physical contact, it is like you have like some boundary which is kind of diffuse boundary, it is a very good contact I am talking of, it is not that one n type and p type I am just physically touching, it is not like that. I mean, whenever you have a junction of the p and n. Okay. So, whenever you have a junction, what happens is you form kind of diode, and what happens is that electrons, because it is the majority carrier in the n side, it actually tend to flow towards the p side, and the holes being the majority carrier in the p type, it has a tendency to move towards the n side, and by virtue of this they create a region which is called the depletion region of its own, even without any applied potential. Okay. I just make a good contact between a p and n type of semiconductor, they will create this kind of depletion region because some electrons from this has moved towards this side, leaving a static space charge in the n side of the semiconductor. Some holes from the p type move towards the n side, leaving some static negative charge in the p side of the semiconductor. Because there are some static space charge created across the boundary, so there is some potential difference which is created automatically. Okay. Now, because there are some potential differences created automatically, one may think that then this itself should act as a radiation detector. Why not? Because if some radiation actually come and fall in this region, they will be immediately get separated in space. Okay. And if I just able to collect them, then I should able to have, in principle theoretically yes, but the thing is this depletion region depth is very thin, it is only few micron. Why? Why they do not spread? Because this space charge, because they are static and they are created, it no longer allow further hole to move towards this side, and this space charge is no longer allow further electron to move this side due to this. Okay. So, due to this they do not spread further, and so there must be some mechanism to extend it to make a practical detector. Okay? Otherwise, this depletion region is only up to the 100 micrometer kind of dimension. So now, why they are called depletion region? Because in this region no free charge carrier can rest in a position where there is a potential barrier. The moment something is there, they will be either going this side or this side. The region of either side of the junction becomes completely depleted. So that is why it is called the depletion region. So let us imagine that this kind of thing, now I connect to some battery in a forward biasing. So I connect negative terminal of the battery to the N type, I connect positive terminal of the battery to the P side. So this is called the forward biasing. So what it will do, the electron will flow this side, the hole will flow this side, and due to this depletion depth will again reduce. So the forward biasing will be having a lots of large leakage current, because always this current is flowing. So it will actually reduce this potential difference further rather. So what we have to do is, we have to apply reverse bias. You imagine if I connect this positive terminal battery up to the N side and negative to the P side, what will happen? This depletion region will be further extended, and then we will be having a large region of this space charge region, and this potential difference will also further increase because of more number of positive space charge, more number of negative space charge, right. So in such situation, if radiation actually fall in this depletion region, immediately they will form electron hole pair and they will get collected. Okay. So you can see this the most useful detector for this semiconductor is the high purity germanium detector. It is high purity is required because this impurity concentration is linked to the depletion depth. So less is the impurity, more is the depletion depth it is possible, and combination of the efficient absorption and high energy resolution. HPG detector are available in varying sizes. So you see this is a standard HPG detector, coaxial, this is used in lab. You can also have handheld portable HPG nowadays. This HPG detector needs cooling of liquid nitrogen, therefore you can see the diwar here. So this is a handheld detector for field application. Okay, you want to go to a site and do some measurements to field, and this is typically used in lab. It is also available in vertical. It is used in planar, like low energy photon spectrometry. When you are using in detecting low energy gamma ray, you go for a smaller detector, planar detector like this. You can directly see the comparison of the gamma ray spectrum of cesium-137 between the sodium iodide and the HPG detector. You can see the HPG spectra is very sharp. So you can another spectra you can see, let us say you have a multi-energy gamma ray spectrum using HPG detector, you can see identify all the gamma ray energies so nicely. But if you measure the same sample using sodium iodide, you can see this finer feature actually you lose. So it becomes challenging for you as a researcher to identify that what are the isotopes present using sodium iodide, okay, for multi-energy gamma rays. Another useful application of sodium of this semiconductor detector is surface barrier detector, which are used for this alpha spectrometry. So alpha is charged particle, they undergo energy degradation in air medium, so you need a good vacuum for doing alpha spectrometry. And lastly, like some neutron detectors, they are mainly gas field detector or scintillation detector you can use. I just covered it separately because neutron is another kind of radiation which also needs detection, but there is no scope to have a very detailed discussion in this 1 hour. But you can imagine you have fast neutron having some few MeV of energy, or you can have slow energy neutron. So what you do basically, you slow down by elastic or inelastic scattering. So this mechanism actually you utilize to have some radiation detector, and maximum energy of the neutron is transferred to proton, and then hydrogenous material are therefore good moderator. So for example, this water, let us say. So water based neutron detector could be very good detector, or plastic based detector could be very good detector because they have low jet elements. And some proton recoil detectors are used for this neutron based measurement, and nuclear reaction are also used for neutron detection. So standard neutron detectors mostly use proportional counter made of BF3 or helium-3 gases, and they make use of this nuclear reaction to produce these charged particle, and then ultimately they detect them. So with this I conclude my today's presentation, and thank you very much for attention.
So if you have any queries, the session is open for queries. Any questions from students? From faculty side? So I have a question actually.
Yes.
In semiconductor detectors, the only part difficulty is getting pure germanium. That's it.
Yeah.
Otherwise, it's very good.
Yeah, yeah. But pure germanium
It's very
making is
expensive.
yeah.
Very
So
expensive.
in BRC actually there are groups who have been actively working on making high purity germanium and making truly indigenous HPG. So it's a big work program going on in BRC because earlier we used to import it and one HPG used to cost like 50 lakh.
Yes.
So we are making an effort to make it indigenous. So in BRC we have progressed little bit. So
Now crystal pulling, germanium crystal pulling, you are trying? Or?
sorry, yeah, that has been going on. That zone refining is going on for many years. But the challenges here are manifold, like at different step you have a chance to get contaminated.
Yes, sir.
So that is the biggest challenge. So I hope that we will succeed.
Yes.
It's not our group, but some other physics group they are doing it. Yeah.
Thank you, sir.
Thank you so much.
Now I welcome Sri G. Srinivas Rao garu for feedback.
Good morning to one and all. We have completed first session in third day of this workshop by a wonderful presentation on radiation detection and measurements by Dr. Sabyasachi Patra. Sir has explained about radiation detectors, their characteristics, types of detectors and their efficiency, and types of scintillators in detailed manner. And overall, Dr. Patra's presentation was informative, well structured and engaging, effectively conveying complex concepts through clear explanation and visual aids. On behalf of all participants and Department of Physics of this college, I extend my heartfelt thanks to the presenter Patras. Sir, thank you.
Thank you, sir. Now we will go for high tea, and all of you should sharply come back by 11:15.
Source of power. That's what I want to convey the message. The comparison of thermal and nuclear power plants, this is already discussed from last 2 days. If you see the 100 megawatt electricity power generation, in the case of the fuel, almost like you have to read the 2 million tons of coal is required if you want to generate the 100 megawatt electricity per year. But in the case of natural uranium, it is only 150 tons of natural uranium, the where we are using in our PHWRs. If you see the waste wise, in the case of the thermal reactors, we are generating almost 0.5 million tons of ash, because that corresponds to about the 4 lakhs meter cube of ash will be generated. The large volumes of sulfur dioxide and CO2, and of course some of the nitrous oxides also will be released. But if you see in the case of nuclear energy, we are generating only 5 to 6 meter cube of solidified high liquid waste that will be vitrified and it will be stored in geo depositories very safely, and about 5 to 600 meter cube of solidified low level waste that can be also concentrated and they will do the remedial measures for that. If you see the area wise, in the case of, because this much ash we have to keep it somewhere, and in the 2 million tons of coal has to be get it from the earth ore. This we required very large area we required in the case of thermal reactors, because the volumes are what are the fuel we are using and what the waste we are generating, the volume will be very low. That's what the small area is sufficient. Especially in the case of like high population density of India, so we have to consider the what are the area also we require to generate this power. The hydel, the relatively clean because it doesn't require any chemical or anything, but only thing is that we require large areas. If you see our Polavaram project where they are constructing, there are so many villages have to vacate to keep our storage the water in the hydel projects. But in the case of nuclear, the relatively we require very small areas. Is the nuclear power is economical? Yes, it is economical. If we are not competing with any other one, then no one will purchase from us. The finally, the nuclear energy whatever we are supplying, it should be economical. We are achieving that also. That all coal resources maybe last for 100 years. That's what we are saying, that if you consume the same rate, then maybe in the future generations they will not get anything power. Hence, we have to explore all other options simultaneously. The comparison of energy release in the chemical reaction, the coal, that is the carbon will become carbon dioxide. The energy released in the chemical reactions, it is only 4 electron volts per atom. But in the case of nuclear fission, if you bombard with uranium-235 with 1 neutron and it will undergo fission, and this process we are generating about 200 million electron volts. Okay, the 1 gram of uranium releases energy equivalent to that of 3 tons of coal or 2300 liters of fuel oil. This already we discussed it several times from last 2 days. The high energy density we are getting from the nuclear fuels. Now, the fuel required for the, suppose if you want to generate the billion units of electricity, in the case of coal, in the case of coal, we required 1,24,000 tons of coal we required, and in the case of oil, we required 83,000 of tons, and the gas we required 96 into 10 power 6 means 10 power 6 1 million, 96 million meter cube of gas we required. In the case of hydel, we required 37 into 10 power 6 tons. If you keep the height of around barrage about 100 meters, this much amount of water is required to get the hydel. But in the case of uranium, with 1% of enrichment, we required only 4.9 tons of uranium. And if you have the 75% fissile atom density enrichment uranium, that amount will be reduced to up to 65 kilograms. You see the 1,24,000 tons, and it is only 4.9 tons in the case of 1% fissile, and it is only kgs. The kgs we are comparing with the million tons of the coal. That is the density we will get it. What is the meaning of nuclear fission? Suppose there one table you keep something, some plastic items. If you break with something hammer, it will be easily break. Suppose you have something harder materials, you have to with a little bit more force. Thus finally we have to break. Of course, there is a spontaneous fission is also there, but in our technology we are using the induced fission only. Now why it is happening? If you take the one uranium-235, that is a naturally available isotope. After absorbing neutron, it gains the binding energy, because before entering to the nucleus, now the neutron is free. Then we are making to the enter into the one shell, one well of potential. This energy water is free is there, it will be released to the compound nucleus. Now the compound nucleus will be in the excited state. The results in oscillations and distortions, and that may lead to the fission. Now when I am bombarding with anything neutron, it will form the compound nucleus. The surface energies are having the forcing to form together, where the Coulombic forces are forcing to the breakaway. Now if the Coulombic forces are more than the surface forces, the fission will happen, and if it is surface energies are surface forces are more, then fissions will not be happen. Now the barrier is there against the fission that act as the surface forces. Now if you see the uranium in the case of uranium, in the natural abundance, uranium-235 only 0.72% and uranium-238 is about 99.2%. The 235, that is the main isotope responsible for fission. The why uranium-235 only undergoes fission with thermal neutrons, but not why uranium-238. the thermal neutron's energy is only 0.025 electron volts. If you see the one neutron is bombarded to uranium-235, this is the even odd, means even number of protons are there, odd number of neutrons are available in the case of uranium-235. When it is forming the compound nucleus, when neutron is added, then one mass number has to be increased. Now in this case both are even. As Savichachi Patra explained, when the even nucleons are there, it will get the additional stability. Now the compound nucleus will get more stable. That's what the energy whatever we are getting liberation because of neutron is collision, this is a 6.4 million electron volts. Now the energy barrier for to break this compound nucleus is only 5.9. If you, even though you are bombarding with thermal neutron, what the energy gained of this compound nucleus is higher than the energy barrier for the breaking. That's what fission will occur. But in the case of uranium-238, it the already nucleus is the even because even number of protons and even number of neutrons. If you add any additional neutron, it is a compound nucleus uranium-239 that is becoming even number of protons, odd number of neutrons. Now the compared to earlier case, now the excitation energy will be lowered because it's already even, it is more stable. Now you are making it little bit even odd pair. The energy of whatever we are getting, it is a lesser than uranium-235 case. That's why it is only excitation energy is 5.5. But whereas the energy barrier for the fission, it is a 6.2 MeV. It is a higher than what the energy is gained by neutron induction. That's what the fission is not possible in the case of thermal neutrons. Suppose if we increase the energy of this neutron, then we can cross this barrier and then fission will occur in the case of uranium-238 also with the fast neutrons. The energy of neutron has to be increased. Okay, the fission of uranium can be induced by fast neutrons. The fissile elements, the uranium-235 undergoes fission with neutrons with all energies, whereas in the case of 238 undergoes fission only with neutrons of high energy, maybe like more than 2 MeV. Now as fission process yields neutrons having low as well as high energy, because when the fission is happened, along with the fission products or fragments, or 2 or 3 number of neutrons are also emitted. It is having the variable energy, okay, the low to as well as high energy. The chain reaction is possible only with the nuclides which are fissile. If you keep the only like uranium-238, the chain reaction may not be continued because all energies are not equivalent to 2 MeV. Some are also available in the lower energy. To maintain the fission chain reaction, we always require fissile atoms, which undergo fission with neutrons of all energies. That's what uranium-235 is the only fissile isotope available in nature. Now if anything reactors we have to construct, but we have to see the uranium-235 content in the fuel. Okay, the fissile elements along with uranium-235 that is naturally available. We have 2 more isotopes, that is a plutonium-239, that is a man-made element. If you in the reactors, when the neutrons are released in the fission process, some of the fission, some of the neutrons are whatever available in the fission process, it will be captured by uranium-238 that is already present in the reactor. It will form uranium-239 and it will undergo beta emissions, 2 successive beta emissions, it will form plutonium-239. It is also fissile element. It is naturally it is not available. It is a man-made fissile element. The same way, further neutron captured by plutonium-239, it will create the plutonium-241, that is also fissile element. Similarly, if you use the thorium as the material in the reactors, we can generate the uranium-233, that is also fissile elements. These all are man-made fissile isotopes. Okay. What is the fatal materials? See, in the case of uranium-238, it is not a fissile material, but we can convert into the fissile material by using in the nuclear reactor. That is called as a fatal material. Okay. The fatal 238 and capture the neutron, it will generate the plutonium-239, that is a fissile. The same way, the fatal element 232 thorium, once it is captured the neutron, it will be generated to uranium-233, that is a fissile elements. The way the atoms are isotopes where we are converted into the fissile materials called as a fertile elements. Since fuel contains both fissile and fertile materials, additional fissile materials could be invariably produced in the reactor along with the power generation, because in the case of fission around 2 to 3 neutrons are liberated. The 1 neutron is required for the maintaining the chain reaction. We have additional neutrons that can be used to convert the fertile material to the fissile materials. What the energy water we are saying 200 MeV, how it will be distributed as per the mass conservations or momentum conservations. The maximum kinetic energy will be carried by the fission fragments because of higher masses, and then the neutrons about 5 MeV, the energy of gamma rays along with these fissions simultaneously various gamma rays also will be released, that is carried about 7 MeV, and the energy of beta particles around 8 MeV, and the kinetic energy of neutrinos will be around 12 MeV. If you add all together, it will be equivalent to 200 MeV. The neutrons produced in nuclear fission are used to initiate and sustain nuclear chain reactions. The once you initiated the fission reaction, the one of the fission neutron will be used to sustain the chain reaction. The rest of the will be used for the conversion or some leakage and other factors we have to consider. That part I will want to explain now. The fission cross section, that is the probability of occur fission reaction, that is the probability of the reaction they will express in the as a cross sections. The physical meaning is of cross section is area that the target nucleus offering for a particular reaction. The area of the nucleus is offering for this particular reaction. Some of the examples I have given, if you use the thermal neutrons, in the case of uranium-233 it is having 531 bonds. The bonds is nothing but 10 power minus 24 centimeter square area. Finally it should be area, unit should be the centimeter square, and uranium-235 it is a 583 bonds, and plutonium-239 about 742 bonds. Now the cross section, how it is the cross section is varying with the energy of neutrons. If you see in the lower than electron volts, the cross sections will be higher. In the case where I am making a straight line, that is the thermal energy, and I have taken uranium-235, that is 580 bonds. If you increase the energy, then there will be, after the reaching some cross the electron volts, there have some resonance capture cross sections will be increased. Then finally it is with increasing energy the cross sections are getting lower, and if you see around 1 MeV region it is only 1.2 bonds. If you increase the energy of the neutron, the cross sections are coming down. You just see that when a neutron is passing very fast, the probability of interactions will be come down. That's what the cross sections are lower. When the neutron is moving very slowly, we have the better probability for the capture. That's what the cross sections are high at lower energies of neutron, and if you increase the energy of the neutron, the cross sections will be lowered. Suppose in the case of thermal reactors, the fissile atom density something whatever we are using, the same fissile atom density, if in the case of fast reactors we can't get the chain reactions. Okay, criticality you will not get it. That's what we have to use high fissile atom density in the case of fast reactors, and in the case of thermal reactors, compared to fast reactors, we can reduce the fissile atom density in the case of thermal reactors. What the definitions? The nuclear fission is nothing but division of a heavy nucleus into two nearly equal parts, the releasing of a large amount of energy. And then the same thing pictorial form I explained here. You see what are the neutrons are generated in the fission, it will be a higher side. Then we have to use the moderator to make it thermalization, and then this thermal neutron will be used to bombard the uranium-235, and it will undergo the fission. And these fissions, what are the neutrons are generated, again we have to do the moderation, and then it may lead to the 3. If you are not able to control, the chain reaction will progress in the very short span of time, that will lead to the explosion. If you are able to control by using some other means, that means what are the neutrons are coming from the fission, only one is allowed to create the one more fission, the chain reaction will be continue. The controlled manner you have to make these fission reactions, then we can use it as a power generation. The nuclear reactor, it is a device in which fission chain reaction takes place in a controlled manner for the production of energy, the heat and neutrons. Now actually what are the energy we are getting, it is in the form of kinetic energy of fission fragments. This kinetic energy has to be converted into thermal energy. the kinetic energy conversion to the thermal and electrical, and then a strong source of neutrons, because each fission is giving 2 to 3 neutrons, and along with only one is required for the chain continuation, that none other neutrons are available. It will create the strong source of neutrons. And the production of isotopes in the research reactors, suppose our aim is to produce the some isotopes, that is called research reactors, then this source of neutrons could be used for the production of some isotopes which are required in our application site. The isotopes, like what are the applications we are going to explain in the tomorrow about the isotopes in medicine, agriculture, industry, and research activation analysis, neutron beam research. This could be used for from the what are the neutrons are coming out from the research reactors. What is the meaning of chain reaction? The condition for chain reaction, at least one neutron released during the each fission should cause another fission. That is called the chain reaction has to be maintained. In the reactor, the which characterizes the fission chain reaction is expressed by multiplication factor, that is the K, is nothing but the number of fissions in the generation m plus 1 that divided by number of fissions generation in the previous generation, that is called m generation. You can use, suppose it is x, this will be x minus 1. The number of fissions are occurred in this present generation divided by the number of fissions in the previous generation. If it is 1, the chain reaction is critical, that is called steady state chain reaction is possible. If it is less than 1, the chain reaction is not sustained, that means it is a subcritical. If it is more than 1, that means the supercritical. In the case of nuclear reactors, we have to maintain the K is equal to 1, that sustained chain reaction in the controlled manner we are getting, that is criticality we are, that generally we must have heard in the nuclear newspapers, this Kaiga plant 3 got the criticality, hot criticality, something like that. The criticality means they maintain the chain reaction, sustained chain reaction, where the K is equal to 1. Okay. For a infinite and non-leaking system, suppose uranium-235 is a fissile and about mu neutrons are produced per fission. Suppose the number is the random numbers, 2 or 3, whatever we are saying. You take it as a mu number of neutrons are released for each fission. Now, for each fission mu neutrons are released, but what are the number, once the neutron is captured, there may be something compound nucleus is forming. Only the sum of the fractions only will be undergo fissile, or some of the fractions will undergo as a compound nucleus will be stable. Now in this we are expressing how many fractions of compound nucleus are undergoing fission, that is sigma f divided by sigma f plus sigma c. Sigma c is the capture, means once you take uranium-235, the once neutron is captured, it may generate to uranium-236, that will may be stable some of the cases. In some of the most of the cases it will undergo fission. The fission we expressed as the probability of fission expressed as a sigma f, and the capture will be represented as a sigma c. Now if each fission we have the mu neutrons, and now that has to be multiplied how much of fraction is undergoing the fission. That's what the number of neutrons released in each fission is equal to mu into sigma f by sigma f plus sigma c. Now the what are the neutrons are released, it may be some of the fast neutrons that may cause the fission in the uranium-238 like fatal elements. Now that correction have to be incorporated here. The epsilon is the fast fission factor like a 238 fissions. It is the ratio of the number of neutrons produced with neutrons of all energies to the neutrons number from the thermal neutron fission. Means the what are the fissions are happening with all energies divided by the number of fissions are happening only with thermal neutrons. That is the fast fission neutron efficiency factor, that is called epsilon. Now after the fission we have now eta into epsilon neutrons are available. To increase the cross sections we have to slow down by using something moderator. But in this process, because it's like an energy like 1 to 2 MeV of neutrons are there, we are making it to thermalization. In this process, different energies of neutrons are available. In some of the cases, it may have the resonance energy of 238, it will capture by some other elements, some other isotopes. Now from that it has to escape. Now we have to see the resonance escape probability, the probability of a neutron to escape during the thermalization. During this thermalization process, some other atoms will be captured. Now we have to see the probability of escape from that. That we have to know what are the number of neutrons available now, eta into epsilon into P, for these are the total neutrons are available. Now in these reactors we have so many other materials including the fuel, clad, moderator, coolant. There some of the neutrons will be captured by other materials also. Now that factor also we have to consider here, that is called F, that is thermal utilization factor, that is the ratio of number of thermal neutrons absorbed in fuel to the total number of neutrons absorbed by all other materials. The chain, to continue the chain reaction, the neutrons should be absorbed by our fuel materials. But there are so many other materials are also there that may absorb also. That's what we have to see the thermal utilization factor. Finally the K infinity will be eta epsilon into PF. That is called four factor formula. You must have listened in your textbooks. The K infinity, why I am saying that, I assuming that the nuclear reactor is infinite and there is no leakage. In the practical case, I cannot make nuclear core like infinite dimensions. There will be some finite dimensions. Then the leakage probability also we have to consider. That is called the effective, K effective. If the lambda is the probability of non-leakage, then the K effective is equal to K infinity into lambda. Okay. The initial case, what we assume that there is no leakage, but always the leakage will happen from the nuclear core. That factor also we have to consider. The K effective will be K infinity into lambda. If the K effective is the 1, it is the sustained chain reaction. If the K infinity is the less than 1, it is called subcritical. If it is the K infinity is more than 1, that is called supercritical. Okay. The major reactor components. Now once we got the chain reactions, what are the different components in the reactors we have to see. The one is the nuclear fuel. Now as I mentioned, to sustain the chain reaction, how many number of atoms of fissional atom is there, what is the cross section of for the fission, and then how many neutrons are available to sustain the chain reaction. These are the reactions are happening. Now when I require the moderator, what the fission neutrons are releasing is are on the higher energy side. We have to get the thermalize. For this purpose we have to use some moderator. It will just slow down the energy of neutron, that is called moderator. Now whatever the heat energy is coming, kinetic energy we are converting into the thermal energy. Finally our aim is to produce the power. The power means we have to generate some steam to run the turbine. Now for this purpose we have to use something coolant, where the heat will be extracted from the nuclear fuel and transferred to our steam generator. This is called the coolant. And then there should be some barrier, because the coolant is circulating. Suppose there is no barrier, from the what the fission fragments are coming out from the nuclear fuel, it will enter to the coolant, then entire coolant will get contaminated. This coolant we are taking to the steam generator, that is outside your core, there also you will get some radiation dose. There should be some barrier to protect the nuclear fuel, to minimize the interaction with the clad, or avoid the interaction with the clad, avoid the interaction with the coolant, sorry. Okay, that is called as the clad. And then there are the control rods, because the chain reaction should be the continue only with K infinity as a 1, then we require something control rods. Suppose if you want to shut down, we can insert in the control rods, we can switch off the reactor, that like the way we are switching off the pipe power, switching on the fan or off, the same way there is some sort of controlling, that is called as a control rods. Then shielding, because the high intensity of gamma rays, these all are emitting from the nuclear core, whereas from the outside we should not get anything those, we require something shielding. This entire one reactor core will be encapsulated in one building, that is called the shielding. Okay. The basic features of nuclear reactors, the core where the nuclear fission is occurring, where we are taking this nuclear fuel and moderator and coolant is called as a core. The moderator for the thermalizing the neutrons, the reflector for the substance sustaining the chain reaction at required power level, because as I mentioned, when the core size is smaller, the leakage will be there. To minimize that, we will always use some reflectors, such that neutrons will come to the core. The control rods, the absorbing of the neutrons to control the chain reaction. Suppose it is becoming the supercritical, then they will insert the control rods to sustain this chain reaction at the control level. The coolant to remove the heat from the core. Then we have the heat exchanger. The coolant is carrying the heat. Their heat will be exchanged to the secondary coolant where the steam will be generated. The reactor housed in a leak tight container, because should not be any leakage from the radioactivity other things. This entire reactor will be housed in a leak tight container. A few meter thick concrete to protect the personnel, because whatever the gamma energies are already discussed yesterday, the interaction will be very less. We have to use the very long thickness of concrete and to avoid the gammas or any neutrons, and we have to use the concrete protector personnel. The secondary containment, in case of anything primary, say something has happened leakage, we have the secondary containment such that at any cost no radiation should come out from the reactor. Then the inbuilt redundancy, around 1.6 kilometers exclusion zone is required in the case of power reactors, and 5 kilometers buffer zone is required only for the power reactors. Both the conditions apply only in the case of power reactors. This is a schematic of the nuclear reactor, what I mentioned. Yeah, sorry. Okay, this entire reactor housed, this is called the core, and these are the containment, and then the secondary shielding is there. Where is the coolant is flowing into the core, the heat will be exchanged and it will be brought down to the heat exchanger. Where the heat is exchanging, it will generate the steam, and this steam will go to the turbine, and then the turbine will move and will get the power. Then now each component will explain. As I mentioned the fuel, we should get the fissile material. We have the 3 isotopes of fissile materials: uranium-235, plutonium-239 and uranium-233. These are the man-made elements, and naturally available is only uranium-235. Now what are the, along with this always fissile materials, we always have to add some fertile material like uranium-238 or thorium-232 to convert this fertile element to fissile elements. Not only the power production, we are generating some of the fissile elements for the next reactors. What are the desirable properties for the nuclear fuels? You should have the high melting point, because in the fuel itself we are generating high energy, then it should not melt, then it should have the high melting point. Then high thermal conductivity, because the heat is generated in the fuel matrix, it has to be generated passed to the coolant, then it should have the very high thermal conductivity, and good thermal stability also, because when I am designing something with some structure, if because of heat treatment is going to some other structure, then it may deviate our the design parameters. The good radiation stability, high fissile atom density, capacity to accommodate swelling due to fission products, the chemical compatibility with clad and coolant, then low neutron cross sections for the associated atoms. Okay, the chemical form, what are the fuel we are using, either in the form of metal or some alloys, oxides, carbides, nitrides, depending on your nuclear reactor design. So one of the form they will use, either in the form of metal or alloys or oxides. Now the cladding, that is actually the containment of fuel and fission products to maintain the predetermined geometry of the fuel. As I mentioned earlier, we require one clad material such that this fission fragment should not be released into the coolant. We should have the one barrier. That barrier is acting as called as the cladding. The desirable characteristics for this cladding material, you should have the very good chemical compatibility with the fuel and coolant, such that when I am started the reactor in some other form, and it should not form to some other reaction products at the reactor operating conditions, you should have very good chemical compatibility with the fuel and coolant, and the low neutron absorption cross section, the high mechanical strength at elevated temperatures, because the nuclear reactors are operating at very severe conditions, very high pressure of coolant and high temperatures. At these conditions also it should have very good mechanical strength, then radiation stability and high thermal conductivity, because if it has high thermal conductivity only, the heat will be transferred from the fuel to the coolant. The materials used, like some of depending on your application, aluminum alloy, zircon, graphite, stainless steel, depending on your reactors they will use this. Some photographs I am showing here. See, yeah, this is the fuel pellet. Suppose if you case our PHWRs, the uranium oxide they will take like a pellet, and this pellet will be encapsulated into the cladding material. This is the clad tube. They will insert this all the pellets together, and then they will seal and seal, and they will make a bundle. These are the actual photographs of our PHWR fuel bundles. These are the fuel clad tubes. In this, In the tube, you imagine some of the pellets they are adding and then encapsulated at the end, and then they will make like a bundle. This bundle will be inserted into the nuclear core, and this is the BWR fuels. This will be used in our Tarapur, and these are the nuclear fuel pellets. What I am saying, uranium oxide pellets. These all are made in our NFC Hyderabad. The coolant, the purpose is the removal of heat from the reactor core. Then what are the desirable characteristics? You should have the low neutron absorption cross section, otherwise the F factor will be higher, such that the cross section should be low to maintain the F significant number of F. The high boiling point, such that the heat efficiency will be increased. The high specific heat, high thermal conductivity, low cross sections for the neutrons, and you should have the low viscosity also, such that I can pump with whatever the pumps are available. If the viscosity is more, then I have to use high power pumps to pump this. The chemical compatibility with the fuel and cladding, as I mentioned earlier. And what are the materials are used depending on your application, like light water, that is normal water we are getting, and heavy water, it is also produced in our neighbor state, that is Telangana in the Manuguru plant. And some of the case, the gas cooled reactions, they will use the CO2 also, helium, and even liquid sodium also could be used as a coolant. The moderators, the purpose is the slowing down the neutrons which are coming from the in the MeV range from the fission to the thermal region like 0.025 by collision with the light atoms. Then it should have the low cross sections for the neutrons, then high moderating capacity and high atom density of moderating atom, low cross sections, high specific heat, and you should also have the chemical compatibility with the clad and fuel other materials. What are the different options I am mentioning here? You have to see the thermalization, how many collisions are required from 2 MeV to around 0.025 thermal energy range. In the case of hydrogen, if you record only 18 collisions and you see the cross section of 0.33. During this process, some of the neutrons will be captured. But in the case of deuterium, the number of collisions may be increased to 25, but the cross sections are very low. If I am using the low enriched uranium fuel like natural available uranium, I have to use the deuterium based moderators as a coolant or moderator. But in the case, suppose I am increase the fissile atom density like enriched uranium, I can go for the light waters. There are some other options like helium, lithium, beryllium, graphite, there is nothing but carbon, and oxygen also we have to see, invariably it will be there with hydrogen and deuterium in the case of waters. Okay, these are the number of collisions required for 2 MeV to 0.025 to brought the energy brought down, and you have to see the cross sections also. Based on your application, we have to choose which of the moderator or coolant. Okay, the moderator used in different reactors, like in the case of natural uranium based reactors like our PHWR, we have to use the heavy water as a moderator. Suppose if you have the enrichment facility, enriched uranium reactors, we can use the light water also. But in the case of fast reactors, as I am saying, the energy of neutron is already fast, we required in the fast region, we don't require any moderators. Okay, where I am saying the fast reactors which is available in our Kalpakam in Tamil Nadu, where we are not using any moderators. The coolants like gaseous like CO2, helium, liquid deuterium like heavy water, light waters in the case of enriched uranium, sodium, fast reactors, organic, molten salt, there are so many options are available. The control rods, when to avoid the criticality factor more than 1 means should not become the super critical. For this purpose we have to use the control rods and reducing the excess reactivity 30%, start up or shut down the reactor, fine control of the power from the different regions of the reactor. The desirable characteristics is high neutron absorption cross section, that is what it will control, what are the excess of neutrons are available, it will capture and then it will sustain the neutron activity will be lower down. The high atom density for the neutron absorbing atom, these are the desirable properties. Okay, these are the options are available like boron, cadmium, silver, these all elements could be used depending on your application. The fuel designers will be designed which of the component they have to use as a control rod materials depending on your application. Okay, the reactor control, the reactivity is K effective -1 divided by K effective, that decreases with the fissile atom decreases, because in the initial case suppose I am using something 100 kilograms of your fissile atoms, with increasing the time the fissile atom density will be coming down. Now it's not like that after certain time it will become subcritical. We have to maintain the chain reactions when they are designing. These are all factors they will see, but at the same time the fission products are also growing up, and some of the fission fragments also have the high cross sections. Always they will see the initial period the excess activity will be there, and then this excess activity will be minimized by inserting the control rod materials. With increasing time, the slowly control rods will be taken up from the reactor core to maintain the chain reaction K infinitive as a 1 or K effective as the 1. The types of reactors, the gas cooled reactors, the way we are using the concept, we have to use the combination of different components, like what type of fuel, what type of moderator. Based on that, these are the namings are there. Like gas cooled reactors means that we are using a CO2 as the coolant, this is called as the gas cooled reactors. Advanced gas cooled reactors, that they have done some modification, instead of CO2 they have gone for the helium gas cooled reactors, that is called as the advanced gas cooled reactors. High temperature gas cooled reactors, if you increase the further temperature of your fuel material, this is called high temperature. Boiling water reactors means in the core itself we are generating the steam in the core itself, that is called the boiling water reactors. In India we have the two reactors of this type in Tarapur in Maharashtra. The pressurized water reactors, like they will take the light water and pressurize, and this type of reactors are available at Kudunkulam. 3 types of reactors are available, and our work hearts of our Indian nuclear energy program, that is the pressurized heavy water reactors. When I am using the natural uranium as a fuel, I have to use the heavy water as the coolant or moderator. This is called the pressurized heavy water reactors. The light water cooled graphite moderator reactors, this is one of the concept. And also we have the liquid metal cooled fast breeder reactors. These are available in the Kalpakam, and then CANDU, that is the thorium based PHWRs, molten salt reactors. There are so many concepts are evolving with the time, and what are the reactors we have in India that I have mentioned here. Okay. The classification of thermal nuclear reactors based on enrichment of fuel. If I am using the natural uranium, then based on the moderator we have to use the only heavy water. When I am using the natural uranium, that is called PHWR. And we have the 2 types of research reactors, Cyrus, of course that is already decommissioned, and we have the Dhruva still that is running in our BRC campus itself, where that will be used for the generation of different isotopes. When I am using natural uranium, we can also use the graphite as a moderator, that is called gas cooled reactors, but now there's this reactors type there, because of some advancement there, no one using this case now. When I am using enriched uranium, we have the light water as a moderator we can use, that is called PWR, BWR. Earlier we have the Apsara, now we have the Apsara U in our BRC campus. Kamini, that is the reactor is available in our Kalpakam. The graphite based, there are different types of options are available. Now just world wise which reactor they are using is not like that the PWRs more, that doesn't mean that they are more safety wise they are more preferable. Depending on their availability, what the technology available, the different options they are explored. The highest fraction is available in the case of PWR, that is a power pressurized water reactors. Just the world wise just given the scenario what is there. And this is the boiling water type of reactors, where I mentioned in the core itself the coolant will get boiled, and this will be transferred to the steam generator, and then the steam will be this turbine will be run the turbine, and then they will cool it out, and the same coolant will be pumped to the core. When I am boiling in the core itself, we are calling the boiling water reactor. The B means boiling water, boiling. The core itself I am doing the boiling. This is the schematic picture of BWRs, and just for your modification I am saying like this. The power will be generated here, it will go to the turbine, and from the turbine power will be generated, and it will go to the grid, and where we are getting the power and will be our lights we are getting. Some schematic picture only I mentioned here. Now it is the PWRs. In the case of PWR, one primary coolant is circulating, it is only pressurized, it is circulating. The secondary heat exchanger, where we are generating the steam, this steam will be transferred to the turbine, and it will generate the power, and then you will get the power here. Then now this same what are the after the turbine running, what are the water is coming, it will be condensed, make it cool, and then again pumping to the steam generator. The heat exchange is happening here. In the case of BWR, this heat exchange is not required. Okay. Then our Indian pressurized water reactors, as I mentioned, is a natural uranium, and we are using the heavy water as the coolant. we have burn up around, this all are parameters are there. These are PHWR schematics, what I am saying. This is the primary containment, the secondary containment, there will be heat exchanger will be there, and then from this they will go to the turbine, and then power generation will be there. Okay, these are the, as I mentioned, this is the core material. Inside the coolant channels will be there. In this, the pressure tubes will be inserted. In that, fuel bundles will be inserted. Some schematics are what I have given here. The fast reactors, as I mentioned, fast reactors means we should not have any moderators. Now, in the case of what the conversion ratio, as I mentioned, some of the neutrons will be used to convert the fertile to fissile elements. That is called conversion ratio, means the ratio of fissile isotopes produced to the fissile isotopes consumed. How many fissile atoms we are consuming compared to how many fissile atoms we are producing. If the conversion ratio is less than 1, that means it is not a breeder. We are consuming more. The conversion ratio is the 0.55 in the case of light water reactors. In the case of PHWR, the conversion ratio is around 0.7. If the breeding is required, that means the conversion ratio should be more. The water that we are consuming, we generate more than that. The conversion ratio should be more than 1. That is only possible in the case of fast reactors. Okay, in the case of like a breeding technology, if you suppose in the fast reactors like a 100 megawatt electricity generation we are using, like uranium, natural uranium or plutonium oxide fuel, initial period suppose you take 3 tons of uranium, the rest is uranium-238, 12 tons. After the irradiation, the nuclear reactor, if you do the reprocessing, we are generating now 3.25 tons of plutonium. Initially we have taken 3 tons, now we are generating 3.25. It will be reprocessed and we can recover the plutonium, and then it can be reused in the again to the reactors. That is the technology wise. The why we are getting the only breeding in the fast region, this all depends on the eta, that is the number of neutrons emitted for each fission. In the case of thermal region, we have only 2.6 is the maximum. That means 1 is required already for the chain to maintain the chain reaction. We have only excess of only 1.6. Out of this, some of will be captured by all other materials, leakage, everything will be there. That's what conversion ratio we are getting only as a 0.7 in the case of PHWRs. But in the case of energy at high around 1 MeV region, we are getting the almost like eta value almost very close to 3. Now only 1 is required for the chain continuation. We have the excess of 2 neutrons are available now. Then that's what we convert more amount of fertile to fissile. That's what breeding is only possible in the case of fast reactors. The liquid metal fast breeder reactors, this is a concept here. This is a core, and the one primary liquid sodium will be passed as a coolant, primary circuit, and there will be one more secondary coolant passing is here. There heat exchange from happen to primary circuit to secondary circuit. The secondary circuit will take out from the nuclear core building. Here heat exchanger will be there. It will generate the steam here, and it will run the turbine, and then this water is continuing like this. Because the liquid sodium is we are using, we have to use one more heat exchanger, primary coolant, secondary coolant. The secondary coolant only we are generating the steam. But in the case of PWRs, only primary heat transport is sufficient. But in the case of when I am using the liquid sodium, we have to use the 2 types of primary heat transfers. These are India's nuclear energy program, and we are using in the stage 1 the natural uranium, and whatever the plutonium is generated, that will be used in the stage 2, and in that case we are using the thorium as the blanket material. We can generate uranium-233, and the stage 3 we will go for that by using the water the uranium-233 we are generated in the stage 2, and then it will be sustained, and now we already entered the second stage, and in the future maybe it will go to the stage 3. We have the energy security up to like 400-600 years also we can run like this. Some of the photographs, the Kakrapar atomic power station in Gujarat. This is the Kaiga in Karnataka, Tarapur atomic power station. There are some of the photographs I have shown. Is the Rajasthan in the Kota, and Madras atomic power station Tamil Nadu, and Narora. This is a fast breeder test reactor at IGCR Kalpakam. The conclusion is the nuclear reactors at safety and reliability is very much good. Economics also it is very viable. And the optimal utilization of natural resources, then we can utilize our thorium, which is a vast resource are available in our India, that could be used in our nuclear reactors and then energy have the security from very long years. Thank you for your attention. Maybe I am already crossed the time. Okay, 1 or 2 questions you may ask, no problem.
Any questions?
Yeah.
Yes.
Sir, the first part of your lecture, not only first part, a series of lectures of this workshop reveals the significance of nuclear energy, and we have to create awareness among the people on this nuclear energy.
Yes.
Why the people are afraid of this nuclear energy in India? What I am asking this question is, before this asking this question, I would like to know from you, what is the fate and status of Kawada?
It's nothing but
Nuclear.
because they don't now have the awareness about what is the nuclear energy. That is the aim of our workshop. We want to create the awareness because they don't have sufficient awareness about the nuclear energy. They are scared about that. Now we want to create the awareness. That's why we are conducting this workshop.
Sir, is there any requirement of plenty water resources to establish these plants, nuclear plants?
Sorry?
Is there any need the plenty of water resources to establish
No,
these
no.
nuclear plants?
See, if you see the Rajasthan and Kota, you must be knowing all this Rajasthan that doesn't have any water resources. Still we have the plants there. Because it's a circulation mode we are using. It doesn't require any huge amount of water resources.
That's why I'm asking you,
you
to avoid the public protest,
No.
why not you choose like Procron, Rajasthan, desert places to establish these projects?
See, as I told you, we require some water for the circulation mode. If I go for the desert, then where I will get for some circulation of water also I will not get it. Na? We require some good amount of water, but doesn't mean that we require very vast sources. But at the same time, I cannot keep in the desert.
Yes, one more question, sir. There is a speculation, not speculation, it may be correct. Plenty of thorium and uranium deposits are available in Rayalaseema regions and the beach sands of northern coastal Andhra Pradesh. How far it's correct, sir?
Yeah, see, we have the monazite sands in our coastal area, like from Kerala to up to Orissa. We have the future plants in our stage 3 where thorium will be utilized in our future reactors. We have the plants and already in the process. Dr. Daniel Babu may be explained further about this nuclear technology, what are we getting.
Okay, sir, thank you.
Okay. Yes, sir.
When Niels Bohr and all invented this technology, the first use was a wrong use. So America used it in Japan. That created a big fear. And then it came down, and when the peaceful application of nuclear energy was done and nuclear reactors started constructing, again two or three accidents happened. This also created the further fear. So basically, even if you see all those accidents, number of people who died because of radiation is very less. Just because of radiation you can count in fingers. So this has continued, but now today the world over there is a nuclear renaissance age, and every country in the world, even Germany, is coming back to nuclear reactors because that is the only hope for reaching net zero carbon emission, along with the whatever he told kilowatt hour per capita consumption has to be achieved. Another fear is because of people fear that radiation is related to cancer. This is another fear. See, there is when you say water can kill you, see, one glass of water cannot kill you. If you are going into sea and sinking, so the amount and the quantity depends. How much radiation you can use. Actually, radiation can be used for good purposes. Entire cancer treatment is by radiation only. If you have to have cancer treatment, ultimately you have to have radioisotopes from our department only. So these type of things people are slowly getting to know. So that is what some public awareness will be required.
Maybe you can ask some questions during the lunch hour.
Okay, sir. Regarding the uranium bundles, how they are prepared and how they handle Yes, I want to know.
See, then they will take uranium oxide powder form and they will make the pellet form by some compressing and then sintering. Finally, what I have shown in the picture, they will get the pellets like with around 1.6 centimeter of dia and around 2 centimeter length. The pellets will be encapsulated in one clad tube. Imagine like one tube, very thin tube, Jerklite 4, and they will add one by one, and then they will seal it. That's the clad preparation they will. If you are so is the Jerklite 4 is the clad tube and uranium oxide is the fuel material. The some sort of alloy zirconium and they will add some other alloying elements and they will make a one thin tube. The thickness is around 0.4 mm. You can imagine how much of thick. So only 0.4 mm thickness will be used. Okay, further you can discuss during the lunch hour. We already crossed the limit. Sorry.
Now I invite Srimati G. Padma Garu for feedback on the session on nuclear reactors.
Good morning, one and all. Sabhaya Namaha. After all these, no words to give my feedback. After attending all these sessions, I feel I need to modify my way of teaching particularly. Thank you very much, sir, for the entire team of BARC who came all the way from Bombay to enlighten us as the light and in the beginning session it goes on the enlightening thousands or crores of lights. The impression or enlightenment you created here is endless, and the legacy I promise you created here is, it should go on continuing without any interruption. Thank you very much, sir. One thing, please. With your permission, I want to mention one shloka from Sanskrit. Acharyat padam adatte padam sishyah svamedhaya padam sabrahmacharibhyah padam kalakramenacha. If the total education we need to learn in an entire life is considered to be one, then a sincere student from a committed teacher can learn only 25% in his entire life. The remaining 25% by the student has to learn by his own hard work, his own intellect, and all that. Remaining 25%, the student has to learn from his colleagues, classmates by means of group discussions or practicals, etc. The last 25%, one cannot learn overnight or in one day or 1 year. It's a continuous lifelong process. And through such workshops, symposiums, seminars, etc., and learning should be a continuous process until one's last breath. Thank you very much for the opportunity given.
Thank you, ma'am, for your feedback. The next session is on DAE technologies for societal applications by Sri Daniel Babu Garu. Now I welcome Dr. C.H. Srinivas Rao Garu to introduce Daniel Babu sir.
Good afternoon to everyone. It is with a great pleasure to introduce today's speaker of third session, Sri P. Daniel Babu sir. So, P. Daniel Babu sir is a distinguished scientist at BARC. He is an electronics and instrumentation engineer from College of Engineering, Trivandrum, Kerala. Sir also holds a postgraduate diploma in software technology from National College of Science and Technology. He passed out 34th batch of BARC training school and has vast experience in process instrumentation and control of nuclear recycle projects in spent fuel processing and waste management. He also experience in prestigious projects like Large Hadron Collider LHC at CERN Geneva during 2003-2004 and played a crucial role in testing of superconducting magnets. He is also an expert software validation and verification for command and control system for nuclear facilities and has authored many guides for computer security for Indian nuclear facilities. At present, he is the head of Technology Transfer and Collaboration Division, BARC, Mumbai. BARC looking after technology transfer activities, Atal Incubation Center, management of activities related to MOUs, Akruti and patent screening. He holds additional charge as head of Public Awareness and Media Interaction Division at Department of Atomic Energy. Today, P. Daniel Babu sir will speak to us about DAE technologies for societal applications. I think it is most informative to us. So I welcome Daniel Babu sir to address the public. Thank you, sir.
Good afternoon, everybody. Thanks for the generous introduction and all. Basically, today you were continuously listening to very deep science lectures. This will be very light, don't worry about it. We are generally talking what DAE is doing and specifically with respect to technologies. So, this is So, this is the 70th year of the Department of Atomic Energy. We have contributed to this country and we are celebrating the 70 years both for the Department of Atomic Energy as well as BARC, which was earlier called Atomic Energy Establishment at Trompe. And we cannot do any lecture without remembering this great man, Homi Jahangir Baba, who actually told that people like us should stay in our country to set up institutions like this. So we were actually the Second World War was good for us that he stayed in our country and we could get this facility. Both are my offices. I work at both places. This is the headquarters of DAE and the other one is BARC. So what DAE does, majorly when you listen, we hear that we do power program. Today, Ramanjelu was explaining what are the different type of reactors. So starting from uranium mining to fabricating the fuel, to designing reactors, to constructing reactors, operating reactors and handling the waste management. The entire circle we call as the power part of it. And in addition to power part, we have something called non-power. We do lot of other things also. It can be a mega science experiment like LIGO or a CERN experiment, which I had the fortune to work there. So we work on research reactors, we work on particle accelerators, RRCAT is there. And then big thing, I will explain that. It is not that we are giving energy security alone. We are giving health security, we are giving water security, we are even giving agriculture and food security to this country. So this we will try to explain in the coming slides. So this was our main mandate to increase the energy mix. It is only 1.6% today. We have to increase it to at least 10% to achieve net zero by 2070, which our Honorable Prime Minister has declared. So we have, thorium we were mentioning, we have 500 years worth, thorium fuel to run our power plants. But we have to come to that stage in the third stage only. We are in the first stage and second stage will go critical within this year. So we have the mandate to make research reactors for studies. We have to take care of medicine, agriculture, industry, cancer care, etc. And I have explained. And finally, the very important thing I would always like to mention, people don't mention it, national security. If the India map is intact like this, it is because of BARC. And how do we do this? We have 6 research centers. I think yesterday Mahapatra Sahib must have explained all these things. So we have BARC, IGCAR, RRCAT and other 6 research centers, R&D. industrial organizations are also there. I'm sorry for the this thing, heavy water plants, then NFC was talked about, and we have also public sector like NPCL, Bhavani and all, which are actually operating the reactors. Then okay, I will just leave it. So this 3-stage program also was explained. Today we are in the first stage where PHWRs are used, natural uranium which we have, which we will be having for another 50 to 80 years with new mines that have come. We will be able to sustain that. Once the fast breeder reactors come, we can make, we can use the spent fuel. Actually, one thing we have to remember is we are following a closed nuclear fuel cycle. The entire waste or spent fuel is being used for either creating more fuel for the next generation, or you are using those fission products for good utilization, which I will explain later. So the entire, he was talking about a high level liquid waste that is being generated. He was talking about 5 meter cube and all. So once I remove the actinides, which actually will be used for cancer care or agriculture, food irradiation, etc., this 5 meter cube can be reduced to size of my ring. So that is the amount of waste that will be created in the same condition. So this is a 3-stage program we are following. So today we are at 8,180 megawatt. Now what is the vision of DAE? Day before yesterday the budget was declared, and we have declared this slide shows 80 gigawatt, but Prime Minister has told 100 gigawatt. So how do we achieve this? The Indian PHWR is the mainstay. Now we have standardized 700 megawatt reactors. So these are the main pillar for DAE. So with that we will make 33 gigawatt. Every next year onwards, every year India will add one more reactor. So within 10 years we will triple this 8,000 to 21,000. That is the aim. And then we have a LWR reactor, as we told, the Russian Kudankulam, and we are buying foreign reactors which will use actually enriched uranium. Even the Westinghouse or American reactors will come. This speed up, what happens is that they have higher capacity, and we can go up to 1200 and 1500 megawatt with this. So this also will be added, because now we are in the nuclear suppliers group. We are expecting more fuel to come here. And one terminology I wanted to add here is budget also it was coming, Bharat small reactor and Bharat small and modular reactor. These are the new type of reactors India is going to design. 23,000 crore has been given for R&D in these fields by Nirmala Sitharaman, Honorable Finance Minister. What is Bharat small reactor? 220 megawatt PHWR, you are making it more, it is the smallest design we have. We are making it more compact, and it will be able to fit it in a NTPC plant when a unit is removed. So NTPC plants, NTPC is also entering the nuclear sector, and the power ministry is also entering into the nuclear sector. So when the NTPC plants which are emitting more carbon dioxide are removed, we will be able to fit these BSMRs there. This is what we have. And small and modular is something different. Modular is when you are going to scale up very large. I should be able to make all these reactor components remotely at the factory and ship to the site, and at the site construction time is reduced, and when you do it in a large scale it will become more economical. At present BSMR is planned for steel industry or cement industry where captive power plants are required. There this is worth. So I think 25,000 will come from there. This is how we will achieve that. So nuclear power, I don't want to explain. What I want to tell is continuously our nuclear power plants have worked for 2 years, 3 years and all continuously without shutdown. So and 629 reactor years means 629 into number of years we have worked, and there was no single incident. So we should be happy about that. And the amount of greenhouse gas emission that has been reduced also is. Now when I talk about energy security, it is not power alone, electricity alone. Hydrogen is the next source. So DAE can produce hydrogen. How do we produce that? We have various methods. We have alkaline water electrolyzers, we have high temperature thermochemical reaction types. What we are doing, why nuclear is connected here is the waste heat that can be generated from next generation reactors. It can be 600, or some of the reactors can be up to 900, 1000 degrees where this thermochemical reaction can be sustained. Iodine, where a sulfuric acid plant is there, we can use an iodine sulfur route or a copper chlorine route to generate hydrogen. So these are the future things that we will be doing. Already we are doing a lot of technology transfer in this area. So many big giants like BHEL and other companies are working with us in this endeavor. So radioisotope is a big thing, and what is our future? We are going to make a reactor only for isotope production. That is coming up very soon in a public-private partnership form near Kakarpa, and this will make India really a Viksit Bharat, matlab world leader in isotope production. That is the plan. Now at present what happens is our research reactor is being used also for isotope production, but this will be a big facility that is planned somewhere in 2037. So as I told, health, water and food security we are taking care. Health security, all the radioisotopes that are not imported, which are actually 5 to 6 times costly, are produced in this country. And we have a facility where from BARC this goes to BRIT. BRIT encapsulates it and packages it for hospitals, and within 36 hours it reaches all the cancer hospitals in the whole country, and 60% of the cancer treatment is by DAE. The cancer grid, 60% of the people are handled by DAE hospitals. So if you see the cancer hospital, Tata Memorial Center is part of Department of Atomic Energy. It is not part of Ministry of Health. So you understand that time itself people understood this, and we are growing in a big way as far as cancer treatment is concerned. So as far as food security is concerned, we know that 40% of the food that is produced is wasted. So what DAE does is that we have technologies where irradiation can be applied, and various things are there, whether it is insect control, then microbial decontamination, or see onion and potato I wanted to mention. See sprouting in onion and even in potato, as well as that blackening and all, how much can you keep in a cold storage? That doesn't work. Whereas if you irradiate it with a minimum dose, we can increase the shelf life of these things by 6 months. So we have proved it with the Ministry of Foreign Food Production, MOFP in Nasik recently, and 3,500 tons of onion was irradiated, and we showed the farmers that this can be done, and we have to have a humidifying facility so that the weight loss is not there. So these are all proven techniques. Mango, for example, one example I wanted to tell, we have extended the shelf life of mangoes to 30 days, because of which what happens, instead of air route, we can take it by sea route to USA, and USA it is mandatory that mangoes has to be irradiated to be exported there, and they don't want the disease making organisms to be shipped to their country. So there is a quarantine barrier which we were able to collect, and farmers in Maharashtra are very happy about this development which we did 2 years back. And how we do this food irradiation is 2 methods are there. Radioisotope cobalt-60 is there, and we can also use accelerators also for this thing. Another big thing we have worked is mutation, breeding of seeds. So if you are eating urud dal and all in anywhere in our country, it must be produced from BRC seeds. So what we have done is lot of seeds which are giving more yield depending on the soil that is taken, and more resistant to climatic pests, insects and all, we can generate using this mutation techniques. And many people confuse with what you call DNA change is not there in this thing, and this has been certified by the Food Security Ministry also, and these are officially released by Gazette after a span of 10 years of testing. So it has been proven, and in the 70th year of our Platinum Jubilee, we have produced 70 varieties. That's a big success, and we will grow to 180 varieties in the Amrit Kal. So water security is another thing. What we are doing is, I will only explain that using a nuclear reactor, again using the waste heat, we can do multiple techniques like reverse osmosis, or you go for the thermo vapor compression techniques, where you can have KLD level of water desalination plants. And India being a peninsula, we have unlimited source of seawater, and DAE can provide drinking water from all these places. So that is the vision, and we have all different industrial household type of water purification methods, water contamination detection methods, everything related to water is available as far as technology is concerned. So how do I transfer these technologies to the industries? So before starting on to that, one thing I want to explain is that DAE has worked under embargo always. When we did the 1974 peaceful explosion, the world isolated us. Again 98 also same thing happened, but we have worked independently. We have produced all our technologies on our own, whether it is running a reactor or running a particle accelerator. What happened in the meanwhile is we developed lot of technologies which were needed to make a reactor. So these technologies are useful for the industry. So we decided to transfer this know-how. So technology transfer division, when a technology is available which has a reliable, what you call readiness level of 7 or something like 6 or 7, we transfer this license to industry. They can buy this license, manufacture that technology or technology process or product, and sell it to industry. So this we are doing regularly. We are also having 4 Atal incubation centers where technology mentoring is done, and something over and above what technologies we have generated is new technologies are developed along with the entrepreneurs. Akruti Kendra is also one important thing as educational institutions, how there is a mechanism to give technology to educational institutions. I will explain. And these are all, now the R&D labs in India are open to all the universities and the students now, because these facilities we are giving through consultancy and services. UGC also has a scheme wherein you can use a reactor beamline facilities or a particle accelerator beamline facilities. So these are also provided. So I was just talking about technology readiness level. When do I decide that a technology can be given to the market? So TRL 1 to 3 is the initial stage when a technology is developed in an academia or maybe even in an R&D institution. The proof of concept comes around 2, 3, and then you start assembling it and you start testing it in the simulated environment. Then you go to the actual environment, and that is 6. And at the level of 7, still now commercialization has not happened. So the basic technology was developed, and then you go to the technology development. Here is where we need the partnership of industry, because as a R&D engineer, I don't understand economics, I don't understand packaging, I don't understand marketing. So we have a tie-up with the industry when actual products are actually made and prototypes are made which can be replicated in a large scale. So this is market launch happens along with the industry. So DAE has been continuously, we have around 200 technologies available in DAE website. This is the website, and we are publishing nearly 20 to 25 technologies every year, and we are generating lot of money also from these technologies. This is the last year, nearly 180 transfers happened to the. So in between what the Atal incubation centers have started, government wanted deep tech technologies to be incubated by even departments like DAE. DAE is the first incubation center that has come in the R&D sector. So we have started 3-4 centers wherein entrepreneurs can come to our place and incubate on our technologies. So I'll skip these things. At RRCAT they are doing well with there is a Section 8 company, AIC Pi Hub and AIC Plasma Foundation at Ahmedabad IPR are also, and BRC, AIC Anushakti Foundation is shortly being commissioned. So this Akruti is specifically for universities and schools and all. I will take two moments for this thing. This is a method by which technologies can be given to universities. It's a non-commercial arrangement. So basically, the Anil Khakotwar, he had this concept of sillage, when the city being transferred to a village. So if in a village technology has to be sustained, lot of things has to happen. So what has to happen is institute like yours, College of Physics, has to be there, where this is the knowledge institution, or from where we will like BRC will give technologies to this Akruti Kendra, and this university will have what you call rural development environment, where you can get up people, entrepreneurs, we can get financial institutions coming here. And basically main thing is that if technology has to be developed, you need people here who knows this technology and who can disseminate and explain to others and hands on. So if the Akruti Center here can dedicate some faculty, all the 200 technologies can be given free of cost in a non-commercial license to the university, and people can around come here and see and use BRC technology. You can explain it in the local languages, even product pamphlets etc. can be given in the local languages. So that is a scheme that we are planning. So this BRC knowledge management group, we sign a non-commercial agreement with the institute, and people around can come and work. You can even charge them, and once you have what you call, I think you have already have an incubation center here. So this incubation center, people who wants to do actual business can take commercial license. So in university cannot take commercial license. The people who are working there or the incubation center can commercialize these products. That is a scheme what we have in Akruti. I think I'll skip those things. So finally, I'll show you some glimpses of technology. I was talking about around 200 technologies. So first one I wanted to show is water filters. I use a water filter in my house, which is a ultra filtration type polysulfone membrane. No maintenance has been done for the last 5 years. Somehow other what you call UV type and all are, compared to that, these are all less maintenance, no power, and better in decontamination. You can remove all the bacteria, and even small large size viruses also are removed by this ultra filtration membrane. And we have also now the nano filtration technologies also. So this is a very popular thing with the gel mission of India. We have 200 villages, we have put water ATMs already, and as far as purification is concerned, that is it. And then as far as groundwater contamination is concerned, all the type of contamination, we have methodologies. This is like fluorine detection. In North India we see fluoride is there in water. So this is an easy technique by which a reagent can be mixed with the water, and using the color scale you know how much fluorine is available. So these are all simple techniques, but quite popular and useful. Similarly, BRC has produced what is called the arsenic removal water filter. It is an irradiated cartridge that is used to remove this arsenic content from contaminated water. This is very popular in most of the North Indian states. So we transfer these technologies to the industry at a particular technology transfer fee. This is a lump sum fee that the applicant has to give, and then he gets a license for 5 years, and then he can use BRC logo to sell these products. So food safety, I think I have already mentioned. A lot of things are happening. This is another technology by which this is not an irradiation technology. It is a simple what you call generally available simple chemicals are used. It's a dip surface treatment by which the pericarp color can be retained for lychee. So this is also very widely publicized technology. See, even electron beam welding machines. So we have this electron beam technology for welding applications up to 12 kilowatt, and various power ranges and applications we have developed this, and this is one example where people have commercialized and used our welding machines. Baba Kavach is technology where which boron carbide tiles is used along with CNT sheet spraying. What happens is the advantage is this is boron carbide is light, and Jawan who is at the border, who normally has to take something like 10.7 kg to protect from an AK-47 bullet, can be protected with something like 6.8 kg jacket. So this is a lightest bulletproof jacket that has been made, and it is continuously supplied to CRPF, BSF and all. This is again BRC technology. So I was talking this alkaline water electrolyzer is one of the most popular technology what we are giving to the industry. As I told, all the giants, whether it is Godrej, BHEL, Thermax, everybody has joined us. Now see, this is an example of a spin-off. 10 meter cube hydrogen and 20 meter cube oxygen we had produced for some application, submarine application. This is a good application for the industry today. So this 10 meter cube we are scaling up to 100 and 200 and going into a commercial level. So these companies are helping us to scale it, because it is not our direct job, but these companies are helping us to scale it to higher levels and meet the energy demands of the country. So this is an STP type of thing, hybrid granular sequencing. In a colony like large colony and all, the sewage water can be treated using this thing. It's a biobead formulation, and it's a simple technique, and single tank itself with a clarifier, without an additional clarifier we can treat water, get the useful component manure out of it, and as well as use the decontaminated water for gardening purposes. These are now being set up in all our colonies, and up to 300 KLD plants have been already set up. I'll show them. Nisarguna is one famous technology BRC has given. Nisarguna basically means giving back to the environment. So what we have done is, this is what we call first a hydrolysis process is done, and then anaerobic digestion is done, where this kitchen waste can be converted it gets converted to two things. It can be converted to methane, which can be used for biogas application, and we also can get all the manure out of it. So these two things reduce, this is waste management technology. Today 250 installations are, tomorrow actually I am signing with the Hotel Association of India, Western Hotel Association of India. They have promised it to put it in nearly 1,000 hotels in India. So this is also happening. Urban waste management, many municipal corporation, whatever actual sewage sludge, I think there are people from RTD here. So this is another technology, irradiation of sludge actually can produce bio gold, what you say. Manure can be produced, and this is also happening at many municipalities. Basically cobalt 60 is used as the isotope to irradiate and then produce manure. This was something I am working and just has been publicized. This is a deep brain stimulator. Basically it is used for people with Parkinson's and all. There is a implant pulse generator that is implanted in the body, and it gives pulses to the brain, and normally these are costing something like 15 lakhs outside. We are able to produce this at 2.5 lakhs. This has been published last week, and we are getting manufacturers who are making this DBS that can be, this we have made in collaboration with Sri Chitra Institute at Trivandrum. So this is one slide I wanted to show. See, the spent fuel I told lot of fertile material is was there which can be converted to fissile material. I get the entire plutonium for the next generation reactor from my spent fuel. Now whatever remaining actinides are there, cesium, strontium, these are again used, and with this we are taking care of a lot of things, blood irradiation, food irradiation, this sewage hygienization. A lot of good applications are being done because of this. So that is why this closed fuel cycle has been very useful for our country. So other technologies I will speedily run through. Super absorbent BRC hydrogel. This is a hydrogel powder. Normally the chemical hydrogels can take water up to 350 times, whereas an irradiated hydrogel, because we can control the properties, this can take up to 550 times water. So if you sow it along with the seeds, this will retain water and irrigation requirement can be drastically reduced. So this is the idea. This I think is hybrid granular and this water treatment plant also I explained. Now for hydrogen, various technologies are there. This is a mixed matrix membrane that is available with BRC, and actually earlier asbestos diaphragm and all were used. Now asbestos is banned. Now we have developed this technology, and this is very popular, and this can be used in alkaline water electrolyzers. Lot of demand. Now this we were talking about this production of oxide single crystal. So this YAG laser production के लिए जो whatever material we were able to pull it from a single crystal, and this technology is also available, and we can produce gems and rubies from this thing. Rapid biocompost is a very good example of wet waste management, kitchen waste management, dry leaves, all these things can be managed using our formulation. In fact, I would like to tell an example. In our colony, there is a temple, and in front of the temple there are some 50, there are 10 buildings, 500 flats. The entire waste comes in 15 drums. You know that smell of waste that comes from our kitchen and all. So the entire, it's just in front of the temple. So we put our formulation along with this kokum and all, absolutely no smell, and within 15 days the entire sequentially these drums get converted into manure. This is only one technique. Even coconut leaves can be dried with this. So this is another popular technology. We are even working in the medical field. See, for hypertension, whatever basic material, certain group of medicine is there that is imported from China. So BRC has developed a alternative to that, OTBN. So this is to kill the, import of certain group of medicine from China. Even Dr. Reddy's had come to us to take this technology. Recently we published this technology by which normally what happens, nitrogen fixation happens with lightning. So we can do it with the air plasma also. So this is another technology that has been recently generated. 20 kilowatt takka power we can generate, by which I can produce nitrates in and which can be used for agriculture. Helium detector also 10 raised to minus 8 millibar liter ka jo whatever helium detection, we have generated the entire system here, and this is available for technology transfer. So basically these things happen because see BRC one division makes something and 20 other people require it. So the person who actually developed should not be punished. So what we transfer it to the industry, and we tell the industry you buy from him. So this is one method by which technology transfer has helped the department. We have SCMs also, so scanning electron microscope. This can be used as universities at the cost of around 45 lakhs. Otherwise imported cost is very high. 45 lakhs we can have basic material characterization, because this has a resolution of up to 20 nanometer. So this SCM is also available. If you go to BRC website, all these further technology details are available. You should remember the website only, www.brc.gov.in/technologies. Simple. Or you go to the entrepreneur corner of BRC website. And Boron carbide is a very precious material which BRCS developed, because of which we could make this even bulletproof jacket, and it is a widely popular material for aerospace and other industries. In fact, I can tell you that we are collecting around crores of revenue in terms of royalty from this product. The royalty what we are charging is only 2%. So you can imagine what is the turnover that company is making. So this is one very popular technology. Now recently we have developed whatever good development that happens in metals, materials, we try to publish so that people can take. This is very useful in steel industries and all. So I am just giving a flavor. I think due to lack of time I cannot explain too many things. So this electromagnetic formation and welding also is another technology we have given to the industry. Even this PCB se jo whatever copper removal for we have this technology to generate copper nanoparticles. So this is another technology. This is useful for manufacturing of sensors and all. So it is getting e-waste. A lot of e-waste is there. From that, how to get the copper back. This is something we use for decontamination in our plants. This is a robot that can do cleaning in a big room like this. It has its own capacity to store water, and it can use feedback from this thing. It can go around plant area and do the cleaning. I think these are available in Amazon for houses also, but this is an industrial one with high capacity and power. So this is a leak detection, a leak arresting device where pipelines and all, depending on the size, you can fix this aperture there, and with one person can immediately stop the leak because of the design that was being given in this. This is a simple case why I wanted to put as whatever designs also we have, we are ready to give it, because when a source has to be transported, how the cast design should be there, we are giving this entire know-how design to industries, so they can copy this design, but the regulatory approvals they have to take on their own. So such type of technologies are also available. Gas sensors, this is a platinum 100 RTD based hydrogen gas sensor. Then this is used for brain surgery and all. Surgery purpose ke liye to find the coordinates with a feedback mechanism to isolate the point and it is an electromechanical coordinate measuring device. So it is used in along with the CNC machine. So this is CNT, I was telling, carbon nanotube. Now we are able to make full carbon nanotube sheets which can be used for battery manufacturing and all. This is also, this actually is using this vapor deposition techniques to make these sheets. Plasma torch, I told a lot of application is there in waste management and waste incineration also. We have the entire air plasma incineration system. So this is based on air plasma torch as well as argon plasma torch. These are available for transfer to the industry. CNT sheet is also. Ammonia sensors. See, chlorine dioxide releasing polymer for water disinfection. This is also another technology from RTDD. Basically, chlorine jo hai disinfection, whatever it can continuously produce for a longer life. This based on this polymer, where we have irradiated this polymer, and this can release clean. This can release chlorine dioxide for a longer time and produce clean water. So this is a recent technique. Only in BRC we can do textile jo waste water aata hai, the color can be changed, and the color can be changed using a cartridge which is irradiated, and if you pass through this cartridge, you can, so this is also being used in a big way in Rajasthan and other places for textile industries, and we are directly working with the industry in textile to set up these plants. Now this budget, last budget I was talking about food irradiators. We have 28 food irradiators in the country. Only 3 are from government, all the 23 are from the private sector. That indicates how profitable it is a business. Only thing is, it is an investment of around 15 to 20 crores, but every state requires 2 to 3. Otherwise, we cannot meet the demand of food irradiation and other this thing. And now government is giving a 50% subsidy for these food irradiators. It's a good I mean business proposition. Technology will be given by BRC, and BRIT will give the source, and a payback period is something like 5 years for this investment. Gamma irradiation plant based on cobalt 60 isotope for food irradiation. So just before finishing off, I will show some of the commercialized technologies. So this is if you go to Bombay railway stations, you will find water filters like this thing using our ultra filtration technologies. This is an RO based one at Mayurbhanj, Odisha, and whether it is Karnataka or Rajasthan border, we have such plants. This hybrid granular, I told the sequencing plant, so many plants have come at most of our colonies. Now it is spreading outside also. See, this is one example where this electron beam welding machine was made by a company, by Artec. So they sell it based and BRC logo will be there somewhere, and they publish. This is a recent released by Cologenesis, this company. They have used our nitrogen dioxide dressing, releasing dressing. So this nitrogen dioxide has this healing properties and lot of good, I mean rejuvenation properties. Irradiated this polymer can be used, and this can be, this is a very novel technology from BRC. This is another tablet which was recently launched. This is a nutraceutical. It is actually cancer when you are treating, especially pelvis and all. The around regions also get affected, other than the organism where you are targeting. So this nutraceutical can help in, I mean, reducing the effect on the nearby organs. So it is called a immunomodulator type of or rejuvenant tablet. So this is I explained this thing. Now this is available in GEM as well as Amazon and all. So products have been coming to market. So this is another technology that people are actually in lab and all to chemistry people will be using this thing, because if you keep lot of toxic and hazardous chemicals within the lab, fumes and all can affect the people around. So this safer will entrap all the fumes, and it is a safe I mean storage device that BRC has designed. This also has been commercialized by a company called BG Tech. So when they sell, they put BRC logo and mention that this technology has been developed by in collaboration with BRC. The soil organic carbon kit also is a very popular technology where people need not go to the lab to actually see what is the soil carbon content in soil. It's a small kit where the reagents are available, and you can do it right at the farm and find out what is the carbon content and decide what fertilizers are required. So we are continuously doing a good job, whether all the areas of security I was talking, and what this particular slide only tells that whatever in a nuclear power plant the radiation is there is we are comparing with 3 sievert is the life threatening dose that can happen. It is a height of Eiffel Tower, and see at this level, up to this level there is no detectable effects. and the whatever public, it is the size of a brick, what limit the ARB has given, and what we get in a nuclear power plant, whether it is a reprocessing plant or a power plant, is just the height of a human being. So this we are taking care of the I mean what we follow the ALARA principle as low as reasonably be achievable. So without any exposure to the public, we are able to do all this work, and we are contributing to this country in a big way by splitting atoms. Thank you.
Any questions? The session is open for queries. If no queries, then I welcome Dr. D. Sanjeev Kumar Garu for the feedback.
Thank you, sir. So, I thank Sri Daniel Babu sir for connecting the science with technology. Being a part of technology transfer and public outreach, he gave a wonderful insights how the knowledge of science can be converted to technology. That is where majority of the science institutes are lagging. People are studying vast variety of information and knowledge, but they fail to link it with the real life, real-time applications. And with this talk, we get enough insights to convert our knowledge into technology. And he gave various sectors of various fields where this bark plays a key role, like in energy security, like Bharat Small Reactor and all, food security, health security, water security, all these fields. Sir has explained wonderfully how the technology is being developed in bark for the welfare of the society, as well as national security, and how this boron carbide is being used to develop armors for soldiers and all. So I hope people have got wonderful insights and connectivity to their knowledge of where they can work in their future life. Thank you, sir. Thank you very much for your wonderful talk.
Thank you, sir, for your feedback. Now we have a QA session. So the resource persons will ask some questions, and students are expected to answer. If not students, then the faculty can also answer. You will have nice prizes.
One doubt, sir, on how this radioactive material is taking care of biodegradation. Nisarguna and all.
Nisarguna, there is no radioactivity. It is a even temple waste management is not a
Good afternoon, everyone. We had a great lectures, very informative lectures. So based on the lectures, I have asked some questions. I think Rajahmundry Government College students are eagerly waiting this session, because yesterday Andhra University students are dominated. Okay, let us see what happened. Okay, rules and regulations. If student will not give the answer, that question goes to faculty. Okay, no group answers. Okay, no group answers, and you have to raise your hand first. We will select from those. Okay. Here the first question. What is a nuclear reactor? What is nuclear reactor? Yes.
A nuclear reactor is a device where control chain reaction takes place to produce electricity.
Excellent answer. Electricity as well as neutrons, right? Very good. Come forward, tell your name and take the gift.
My name is Vandana. I am from Department of Nuclear Physics, Andhra University, Visakhapatnam.
Andhra University. Come on, Rajamundry Government College. The next question is, what is the main aim of Nisarguna? Nisarguna, what is the main motto of Nisarguna? You raise the question. Take the mic.
To produce biogas from kitchen waste products.
Yes, excellent answer. Treatment of biodegradable waste to produce gas, biogas.
My name is M. Gopal Krishna. I am studying second MSc Physics. I am coming from Government Autonomous College, Rajamahendravaram.
Okay, next question is, what is the moderator for fast reactor? You have to justify your answer. What is the moderator for fast reactor? You have to justify your answer. That's good. Yes. No group answer?
No moderator, sir.
Yes, correct answer. Justification. Why? Why no moderator?
Why no?
Okay, please come forward. Please come forward. In fast reactors, we are using fast neutrons. So, though there is no need of thermalize the neutrons. That's why there is no use of moderator.
I am Rupa from Adhika Vinana University, MSc Physics, second year.
He has already given the answer.
What does the moderator do?
Kinetic energy of neutron will be reduced.
Next, it's from radiation detection. So, interaction of radiation with matter. What happened? When radiation interacts with matter, what happens? Yesterday I told, when radiation interacts with matter, what happened?
Some chemical changes will be observed.
Sir, please sit.
Let's wait for the students.
Produce positive ions and electrons.
Though two major process.
Ionization and de-excitation.
Okay, not de-excitation, excitation.
Excitation.
Okay, please come forward. When radiation interacts with matter, two things happen. First is ionization and second one is excitation.
I'm Stella from Government Autonomous College, Rajahmundry.
The next question is, what is the energy resolution in the point of detectors? What is energy resolution of the detector? What is meant by energy resolution?
I think ability to detect the energy radiation from the nucleus. Ability to detect
That is detection. What is the resolution?
resolution. No, sir.
Like more is the narrow the curve, the more is the energy resolution factor for the particular ion or the charge. Like the more it will narrow, it will contain some like distinguished values for the particular scattering ions.
Next question is, tell me any three characteristics that coolant should have in nuclear reactor. Characteristics of coolant in nuclear reactor.
Thermal conductivity, low boiling point, high melting point.
Coolant doesn't have melting point.
Low boiling point, sir, high thermal conductivity and nuclear stability.
Next, anyone?
High boiling point, high specific heat, high thermal conductivity, low viscosity.
Yes, very good answer. Very good answer.
My name is Banu and I am from Government College Autonomous Rajahmundry. I am studying MSc Physics in Department of Physics.
Next question is, which uranium isotope undergo fission reaction with all types of neutrons, all energies of neutrons? Which uranium isotope easily undergo nuclear fission with all types of neutrons?
Uranium-235.
Yes, correct answer.
My name is V. Sampurna. I am studying Government Degree College, Autonomous Rajahmundry. I am studying first year MSc Physics in
Today Rajahmundry Government College students are on fire. Okay. Next question is, what is PMT in detector material? What is PMT? Full form of PMT. Yes, correct answer. What is the use? What is the use of this PMT? See, the name itself suggesting photo,
multiplier.
Multiplier to multiplier. It's a multiplier of photons. Okay, right answer, please come forward.
Myself, Dharani. I am from Andhra University. I am studying MSc Nuclear Physics Department.
So next question, what are the advantages of GM counter, and tell me the limitation also. Advantages and limitation of GM counters. Advantages of GM counter and limitation. We did experiment also. 2 advantages and 1 limitation is sufficient.
Low energy ni detect cheyadaniki gamma rays.
Inka?
లో ఎనర్జీని డిటెక్ట్ చేయడానికి గామా.
ఇంకా ఎనీ అదర్ అడ్వాంటేజ్? Anybody else?
It can detect all types of reactors.
Good,
Radiation.
Very good.
Low cost device.
Very nice. What is the limitation? Limitation. Please come forward. What is the limitation?
You know limitation?
Energy cannot be detected, sir.
గట్టిగా చెప్పమ్మా.
Energy readings cannot be detected, sir.
GM counters are having high dead time comparatively other detectors.
My name is Triveni. I am from Government College Autonomous Rajahmundry, first MSc Physics.
Myself, I am Yashashwini, studying BSc second year from Government Autonomous College.
Now listen carefully. Next question. What is the most important characteristics of control rods used in nuclear reactor? Most important characteristics of control rod.
Shielding.
No. Next, anybody? What is the most important characteristic of control rod? Control the power is not characteristics. Control rod ki undavalsina main character enti?
Yes.
High neutron absorptions.
Excellent answer. Very good. Please come forward. High neutron absorption cross section.
I am G. Manvi from the Adikavi Nannaya University campus, Tadepalli.
So coming to next question. What is the role of moderator in nuclear reactor? What is the role of moderator in nuclear reactor? Nuclear reactor lo moderator yokka role enti? Em chestadi moderator?
Slowing down the neutrons from MEV to thermal region.
Yes, excellent answer.
Very clear.
I am Kavya from Adikavi Nannaya University, Rajahmundry, Department of Physics.
So next question is, as sir told, Daniel sir, we have different stages of nuclear program. At present we are in at what stage? At present?
Let's wait. You already
Anybody?
got one. Anyone? It's not second stage.
There are
Nobody answered.
anybody?
Second stage, sir.
Second stage. Yes, correct answer.
Myself, I am Yashashwini, BSc second year, Government Autonomous College.
The next question is, what is meant by detector efficiency? What is meant by detector efficiency? Detector efficiency అని మనం explain చేయండి. What is? Please raise the hand. Sir.
Sir, efficiency is how much gamma rays detected in a detector. If 100 gammas is emitting from the source, so how many detected by detector?
Yes. The ability to detect the radiation.
My name is Adil. I am from Nuclear Physics, Jnanananda Laboratory for Nuclear Research, Visakhapatnam, Andhra University.
Andhra University. Congratulations to all who won the prize.
So all of you please wait for a few minutes. So now we are going to felicitate our chief guest, Dr. P. Daniel Babu sir. So please come on to. So all the faculties from Department of Physics, please come on to the dais to felicitate our today's speaker, Dr. P. Daniel Babu sir. Sir, please come on to the rest. Please sit. Sir, Ramanjani sir. Sir, please.